Hello, good morning, everyone. So, yeah, Tonaya, I can see ready. The first chairperson it was Onu Kumari. Is she online already? No, no. So, Ribu, hello. Ribu, are you there?
Yes, ma'am.
Yeah, just check that when Anu will be online, just explain quickly that she has to read the chat box for question answer session. Just to explain, okay?
Okay, I see someone named Anu who is in the participant list in Zoom. Is that
Okay.
Anu
Then
Kumari?
she should be online. And
Yeah.
after Anu, there will be Naina. So if both of them and Kathakali, I think these Kathakali I can see. Yeah. And Anu is if Anu, are you online? Hello, Anu.
Ma'am, actually, I'm a participant. I'm a poster presenter.
Yeah, but you are chairing the session. You know that first half in the morning.
I guess there is some other Anu also.
Huh? No.
Wait. What is your name, please?
Anu Kumari.
Yes, you are the chair
Uh,
because the poster presenter are the chair. We made it.
you got a mail, right, for the chairs?
Let me check.
Oh. I think you are the one because there is no other Anu Kumari, I guess. And is Naina around? Naina Das, right? Onu, have you found your email?
Yes, ma'am.
Okay, so you are probably the first person who are chairing after inauguration.
Okay, ma'am.
Okay, so the point is that every speaker will get 25 minutes plus 5 minutes. So you have to, I mean, nothing. I mean, you just sit with your mobile or some, watch and just check after 20 minutes or so. You can write in a chat. There is a chat, right? Option down. Okay. Can you see the chat option down, Anu? Down in the are you in Zoom in the mobile or in a laptop?
I'm in a laptop.
Yeah, so in the you go down where there is a mute, stop video option, participants, and there is a chat option. Share screen option. Yeah, so Ganesh has just sent a message so that you can see. Can you click on that chat option?
Yes, ma'am. Here is a message.
Yeah, so there you can type to the speaker that 5 minutes left. Okay.
Okay, ma'am.
So that the people know that there is only 5 minutes left, and the speaker will know. So when it's 20 minutes, you can write that just 5 minutes left, and that will somehow, I think they can, or you can tell whatever they prefer, and then 25 minutes you should stop. Okay, I mean, stop is you request them to stop, and then maybe they may take 1 or 2, but we should finish by half an hour. As you know that this is a virtual online conference, so we should be very strict with the time. And then after this was done, then in this chat box, the questions will be typed by the people, and you have to read these questions one by one. Okay.
Oh, okay, ma'am.
And that I mean, you will have only 5 minutes time for discussion. And so, depending on the time, you have to look at the watch, and depending on the time, you stop. Like after maybe there can be 10 questions, but you choose just to ask first two or first three, because of the time. Okay.
Okay, ma'am, just for 5 minutes.
Yeah, that is 5. So 25 plus 5. Okay. And you strictly follow this thing. Okay. So first three talks, you are this chairperson, and then Naina, are you around? Hello, Naina Das. Rivu, can you check whether Naina is around or not?
No, ma'am, not yet.
Not yet, no? Okay, so maybe quickly, if she is around, you can tell. Kothakali, you understand, right? What you
Yeah,
have.
ma'am.
Okay, so you are in
Am
the
I
afternoon.
audible?
Yeah, you
No,
are
no,
audible.
not yet.
Okay.
So in the
Thank you.
afternoon sessions, you are chairing. So I think whoever is sharing any session, I have already explained, but first one, two is crucial. After that, you people will know. Okay, I'm stopping because I have already told off, and it's already 9:10. So, Rivu, can you take care that when Naina comes, you just have to tell this?
Yes, ma'am. I'll
Okay.
take it.
Ma'am, I have one question.
Yeah, quickly.
Ma'am, the speaker's detail, the affiliation, what he is doing, we
Uh,
don't have that information.
oh, that's a good question.
Uh,
Okay, maybe that's actually also probably Anu doesn't have. So
This we can't do it now. I think we just tell the speaker's name and that's all.
yeah, you just tell the speaker name and the maybe title of the talk, which you can see from the schedule. That's a good point. Maybe we can try from tomorrow or something. If you know someone personally, you can tell.
okay,
I think
okay.
in your case, it's
From the
easy.
first slide, maybe just one thing. Sorry.
Yeah, Shaptashi, go ahead. Shaptashi,
Yes,
go ahead.
from the first slide. If the affiliation is written on the from the first slide, if the affiliation is written, then one can just
Yeah, if the person shared the screen, then you can read that. Okay. So
Start at 9:15 sharp. Or
Well, Pinaki said that he will come at 9:20 and probably he may come a bit earlier and then we will start at. But he wanted to start at 9:20.
okay, so we'll start at 9:20 sharp.
Yeah, you start at 9:20 sharp. It's a one-liner before Pinaki starts, right?
Yes.
Yeah.
Is Naina around or?
Ma'am, I cannot see her. Ma'am, can you just check your WhatsApp once?
Hello?
Can you just check your text once?
Yeah, if Naina is not around, then maybe we can swap with Kathakali because Kathakali is there. Because there can be a confusion like Anu has, who is sharing and so on. So, Kathakali, can you do that if Naina is not around?
Yes, ma'am.
Yeah, so that you can share the from 11 and then Naina can take care from 4:30 if she is not around.
Okay.
Galaxy M31. Who is that? Any idea?
Can you repeat, please?
Hello?
There is one Galaxy M31 showing in the tiles of participants. Any idea who is that?
No.
Hello.
Yes.
Hello.
Good morning. I'm participating from AAA Bhubaneswar, but I don't know why it's showing Galaxy. My name is Hanuja Devadarsini Mohanty.
Okay. Fine.
Okay.
We start.
Is Pinaki online?
Yes.
Yes, ma'am. Sir is online.
So good morning, everyone, and thank you all for being present. Now I request our director, Professor Pinaki Majumdar, to inaugurate the program.
Okay, so can you hear me?
Yes.
All kinds of strange sounds. So, good morning. HRI is a small institute, and when we have the QIC meetings, when we used to have the QIC meetings, there were major events in our calendar. They brought in a lot of people, and there were times when it almost doubled the population of the campus. Now, we were looking forward to that happening in March this year, and then the pandemic hit. We just stopped, I think, a couple of weeks before the program was scheduled. And it was not clear if and when the academic. So over time, the world has learned to use online meeting, and QIC has been quick to adapt to it. So this is the first virtual meeting HRI is having in the post-pandemic session. Welcome once again. Now, virtual meetings have a convenience. So you don't have to travel. There are no logistics with food, accommodation, etc. And a lot of people who could not have attended otherwise can join in. Those are the pluses. But you also miss the warmth and personal contact in these large gatherings. And that human contact is probably the key to any such interaction. Anyway, but just having the online meeting is still a fight back against the virus and sort of claiming the space for ourselves. Small caution and an apology, our internet, Ujjal may have told you, is a bit patchy, has been patchy over the last month or so. We're going through, bad things happen simultaneously. So COVID and then internet. We're going through this difficult phase, and we hope that for the next 4 or 5 days when you have the conference, the internet is stable, doesn't cause disruptions. But things might happen, hopefully for only a limited period. If there are failures, please bear with us for a while. We will try to get it up as quickly as possible. So you will miss the ambience of HRI, the boat ride, and the food that QIC organizes. Maybe very soon next year. For the moment, just enjoy the meeting. And thank you. Aditya.
Thank you, Pinaki.
Yeah.
Tonayash, you would like to add something before?
Yes. So let us thank Professor Majumdar for his gracious speech. Now, since the virtual mode is new to many of us, let us establish some ground rules to keep the talks as smooth as possible. Number one is, please keep your microphones muted and video off throughout any talk, unless of course you are the speaker. Number two is, if you have a question for the speaker, please write it in the chat box if you are on Zoom. Please write it as a comment if you are on YouTube. There is time allotted for question and answer sessions after each talk. And our moderators and chairpersons will get back to the speaker with your questions one by one. Not all questions can be addressed as we would like to keep to the schedule. Please do not write anything but academic questions in the chat box or comments to avoid confusion and cluttering. And number 3 is, if a speaker gets disconnected during his or her talk, we wait for 5 minutes. If he or she is unable to reconnect within this time, we move on to the next speaker. We'll of course come back to the unfinished talk at a later time on the same day. If the speaker cannot reconnect the whole day, we'll try to accommodate the unfinished talk later. Thank you.
Okay, so I think after Tanaya, now Anu will be chairing the session, Anu Kumari. So Anu, are you ready?
Yes, ma'am.
Yeah, okay. So now you start the program.
Okay, ma'am. Ma'am, at 9:30 or no?
You can start now, I mean, yeah.
Okay, ma'am. So our first speaker is Swati Kumari. So ma'am, if you are online, please share your screen.
Hello, Anu. Is it sharing? Is it shared, my screen?
Not yet.
Not yet.
I think now it is shared.
Yes.
So
You
I'm
have to
going
make
to
it full screen. Yes.
Okay. So very good morning to all of you. And am I audible? Sir?
Yes, yes, ma'am.
Yes. Yes.
So very good morning to all of you. And I'd like to thank the organizers, the QIC group at HRI, for organizing this online conference. Now we come to our discussion, and the title of our talk is Proving Inequivalent Form of Leggett-Kirk Inequalities in Subatomic and PT Symmetric System. So, and here is the outline of my talk, where we give the brief introduction of what is macrorealism and Leggett-Kirk inequalities. Leggett-Kirk inequalities have been derived to show the incompatibility between macrorealism and quantum mechanics. Then we discuss inequivalent form of Leggett-Kirk inequalities. That is especially Wigner and Clauser-Horn form of LGS, and we'll also see that how they are inequivalent and stronger than the standard LGS. Then I will discuss one of my results, that is inequivalent form of Leggett-Kirk inequalities in subatomic system, especially in neutrino and meson system. And then we'll discuss PT symmetric system and violation of LGS. Finally, I will summarize all my results. So these are the work involved in this talk. And, so microrealism and Leggett-Kirk inequalities. The whole work of microrealism involves or trying to find out the answer of the question that in which limiting condition, large mass, large size, high quantum number, high dimensional system, the classical results can be recovered from the quantum mechanics, or is there any boundary between the classical and quantum system? We are certainly not concerned in which limit the mathematical structure of quantum mechanics reduces to classical mechanics, but how does the everyday worldview about the nature of reality emerges from the quantum mechanics? Historically, this question was first posed by Schrödinger through his famous cat paradox, that when does a macroscopic system stop existing as a superimposition of states and become one or other state? However, Heisenberg proposed a cut, but he remained silent about the cut, that how this cut can be obtained within the very formalism of quantum mechanics. So these are the experimental approach to answer this question, that a large molecule C60 and its compound is observed in so the macroscopic quantum coherence in these different experiment. And another approach within the quantum mechanics is decoherence, proposed by Jurek in 1991. In the decoherence, system interacts with the environments and it leads to classicality. And another approach is coarse grain measurement. Here, by putting the constant on the measuring apparatus, the classicality emerges. But these approaches do not answer the fundamental question that how, whether microrealism is in principle compatible with quantum mechanics or not. So the microrealist model proposed by Leggett and Gerg, analogous to the Bell's approach. And the assumption of macrorealism consists of, it has two main assumptions, macrorealism per se and non-invasive measurability. Macrorealism per se says that a macroscopic system which is available to it two or more macroscopically distinguishable ontic state will be in definite state at all instant of time, where the non-invasive measurability tells that the measurement doesn't affect the state itself or its subsequent dynamics. On these two assumptions, Leggett-Gerg inequality has been derived. So let us consider the simplest LG scenario of three measurement in a two-level system, where measurement of observable M is performed at three instant of time, T1, T2, and T3, which in turn measurement of observable M1, M2, and M3 respectively. So from the assumption of macrorealism per se, the measurement of observable M should produce the definite outcome plus or minus 1 at these three all instant of time. And non-invasive measurability tells that whether the measurement of M2 or M3 will be affected by the measurement of M1 and so on. So using these two assumptions, MRPS and NIM, the following inequality can be derived, which is well-known Leggett-Gerg inequality. And whether this correlation M1, M2 can be computed using this formula, and similarly other correlation can be calculated. Now we examine the validity of this inequality in quantum scenario. The following so for that, let us consider a simplest quantum scenario where the qubit state is given by this, and observable we take sigma z, and Hamiltonian is governed by sigma x operator, and M2 and M3 can be obtained by this, and unitary evolution between the two measurement can be obtained using this formula. And if we take equal interval of time between the two measurement, that is this quantity is equal to g, then we get the expression of standard LGA 2 cos g minus cos 2g. So we can see from here that this is expression of standard LGA is independent of theta and phi, that is state parameter, and it is independent of the state. And if we take g is equal to pi by 6, then we get the maximum value of this expression standard LGA, and it is 1.5, and that is greater than the classical bound of standard LGA. Hence the Leggett-Gerg inequality is violated in quantum mechanics, and we can say that microrealism is incompatible with quantum mechanics. So these are the experimental tests of standard LGA using different physical systems, that is electron spin, NV centered, NMR, photons, and cesium atom. Now we discuss the inequivalent form of LGS. Here we discuss two form of LGS, Wigner and Closure form of LGS. So this is the key point, that Arthur Fine showed that for a two-party, two measurement per party having two outcomes of each measurement, the only relevant Bell's inequality is the CHSH form, and any other form such as Wigner and CH form of inequalities reduces to the CHSH inequality. And standard LGIs are often considered to be the analogous to the CHSH inequality, but we have showed that the Wigner and Closure form LGS are stronger than the standard LGS. So let's see the derivation of Wigner form of LGS. And the satisfaction of macrorealism implies the existence of joint probabilities, this 3-time joint probability, and pairwise probability can be obtained over by the marginal over this joint probability. And similarly, other pairwise probability can also be obtained. And using these pairwise probability, this 24 Wigner form of LGS can be derived. So we have written it in the compact form. For different values of M1, M2, M3 plus minus 1, we can get 24 inequality from this equation. Now we compare standard LGI and Wigner form of LGI in quantum scenario. So the quantum scenario we have taken earlier. For that scenario, if you plot standard LGI minus 1 and WLGIs, then at G is equal to pi by 6, we can see that this red plot is for standard LGI and blue, and this green plot is for WLGI. So we get the violation of standard LGI and WLGIs. But at G is equal to pi by 4, we don't get the violation of standard LGI, but we get the violation of WLGI. Hence, from this result, we can say that WLGIs are stronger than the standard LGIs. Now we come to the derivation of another inequivalent inequality. And for that, we can obtain the single marginal probability from this joint. And by combining single and pairwise probability, we can derive 24 inequalities. So it is in the compact form, and for different values of M1, M2, and M3, we can get 24 inequalities, and we call them CH form of LGIs. Again, we compare the CH form of LGIs and standard LGI in quantum scenario. So if we plot standard LGI minus 1 and CH LGI as G is equal to pi by 6, then we get the violation of standard LGI and CH LGI both. But at G is equal to pi by 4, we don't get the violation of standard LGI, but we get the violation of CS form of LGIs. Hence, from here we can say that the standard LGIs is stronger than the CH LGI is stronger than the standard LGIs, and these are the numerical results. Now we will prove it analytically. So let us see that. For that, we take this 3-time joint probability in quantum mechanics in terms of this correlation function, and pairwise probability can be obtained as this in terms of correlation function, where this M31 is measurement of M3 is disturbed by the measurement of prior measurement M1, and this M32 is measurement of M3 is disturbed by the prior measurement M2, and similarly M21 is measurement of M2 is disturbed by measurement of M1. So if we put this expression in this Wigner form of LGS, then we get this expression, that is quantum expression of standard LGS apart from these two terms, and which may not be zero, at least for some states. Hence, we can say that Wigner form of LGIs are stronger than the standard LGIs. Similarly, corresponding to 24CH LGIs, yes, we can get this expression. If you put the pairwise quantum probability in expression of CH-LGI, then we get this expression, that is quantum expression of standard LGI apart from quantum expression of standard LGI, we get these three terms. So which again may not be zero, at least from some states. Hence, we can say that the CH form of LGIs are stronger than the standard and Wigner form of LGIs. Now we come to we will discuss the first result of this talk, the probing inequivalent form of LGIs in subatomic system, or more precisely, Wigner. We study here the Wigner and CS form of LGIs in neutrino and meson system. So let us discuss the dynamics of neutrino system. For three-flavor scenario of neutrino oscillation, we can represent a general neutrino state either in the flavor basis or in mass basis, and the state can be represented as this, and the expansion coefficient in these two representation can be connected using this PMNS matrix, where this U alpha K are the elements of PMNS matrix. So, and this matrix can be parameterized in many ways. One of them is given by this, where this coefficient Cij is cos theta ij and Sij is sin theta ij. And these parameters theta ij and delta are the mixing and CP violating phase. So now we can connect the flavor state at time t0 to and some later time t as this, with this flavor evolution operator UFT. So this is the dynamics of neutrino in vacuum. If you consider the dynamics in matter, then this UFT flavor evolution operator will depend on another parameter also, mass density parameter, and we'll incorporate this in our result later. So, and the dynamics of meson system. So meson system is decaying in nature. So its dynamics is governed by open quantum system, and the state after time t is represented in terms of cross operator formulas. And with this constraint, now we consider the quantum scenario of neutrino system. For that, we consider the initial neutrino state as this, and the dichotomic operator as this. So with this, where identity is this summation of all these basis state, then we get the quantum expression of standard LGI as this. So these probabilities are the P alpha is the probability of transition from flavor state nu beta to nu alpha at a time t, and this beta term is non-measurable term. So this is very difficult from the experimental point of view, and one can bypass this non-measurable term by if we assume the stationarity assumption instead of NIM assumption in macrorealism. But in that case, our dynamics will be more constant. So interesting, the inequivalent LGIs, this WLGI term comes out to be independent of this non-measurable term on it, and it comes in terms of transition and survival probability only. So this is very interesting feature of this WLGS. And another interesting feature is we can see from the plot, that is these are the different plot for different neutrino experiment, T2K, NOVA and Dune, and where the expression of WLGI is plotted for different neutrino energy and with respect to different CP violating parameter. that is this is delta 4, delta 0, delta 45, and delta 90 degree. So we can see from this point that the maximum violation of this LGH occurs at the energy around the maximum neutrino flux. So so that is very important from the experimental point of view. Now, if we find the expression of C as LGA in quantum scenario, then for this value, one of the suitable CHLGA is this. Again, it is independent of non-measurable term, and another useful CHLGA is this one. And if you plot this CHLGH with respect to neutrino energy and CP violating phase, then we can see that it's for different neutrino experiment. Then we can say that this violates for all values of delta. And if we plot it with respect to energy for fixed value of delta, another CHLGH with respect to neutrino energy, then again we can see that the maximum violation occurs at the maximum neutrino flux. And from here we can see also that it gives the higher amount of violation than the Wigner form of LGS. In the case of Wigner form of LGS, it was 0.04, and in this case it is 0.05. So CHLGS showed the higher violation than the Wigner form of LGS. And now we come to the dynamics of meson system. So for that, we consider the initial state as this and operator as this, and we can most suitable WLGI is found for these values, and CHLGI for these values. The quantum expression of this was very lengthy, so I didn't put it here. And but we can see from the plot that here there are two interesting features. Again, the CHLGH, so the higher violation than the WLGH, and meson system is decaying in nature. So one other interesting feature we can see that this decoherence, so this blue plot is without decoherence and red plot is with decoherence. So decoherence reduces the degree of violation of WLGH in both these plots. So this is another interesting feature which is nicely manifested in K-meson system. Now we'll discuss another result, that is PT symmetric evolution, maximum coherence, and violation of LGS. So here we'll see the violation of LGS in non-Hermitian system, and PT symmetric is one of them. So we consider the PT symmetric Hamiltonian as this, and where gamma is the gain loss parameter and J is the coupling constant. So where J greater than gamma and J less than gamma and J is equal to gamma, corresponding to the PT symmetry phase, PT symmetry broken, and exceptional point respectively. So, and the time evolution of the state from time S to T is given by the Schrödinger equation. And this unitary evolution is not Hermitian. So we normalize the state after time t, and normalized state after time t is given by this. And now we define another term, that is coherence. So this L1 norm is one of the measure of coherence. So the coherence can be defined in terms of off-diagonal elements of the density matrix as this, where this is bounded by 0 and 1, where 0 corresponds to the mixed state and 1 corresponds to maximally coherent state. Now let us, for our purpose, let us consider the initial state as the maximally mixed state, and the state after evolution is rho Duality. So if we calculate this coherence of this state after evolution, then it can be obtained as this. So here alpha is gamma by j, and and alpha is equal to 1 corresponds to the exceptional point. So in the limit alpha tends to 1, and for large tau, this expression of coherence tends to 1, that the coherence reaches the maximum value at the exceptional point. So now we check the complementary relation between the coherence and this mixedness, where mixedness is defined as this. So for our evolved state at time t, if we calculate the mixedness, then we'll get this expression. So we can see from here that if alpha tends to 1, that is at the exceptional point, this mixedness is 0. So our coherence is maximum at the exceptional point, and mixedness is 0. So the coherence and mixedness are in accordance with this complementary relation. And we can say that the maximally mixed state subjected to PT symmetry dynamics becomes a pure state at the exceptional point. So we can see it from the plot. This coherence is plotted with respect to the alpha and tau parameter, and we can see that at alpha 1, this coherence is maximum. Thus, this maximally mixed state subjected to the PT symmetric dynamics becomes the pure state at the exceptional point. Now we see the violation of LGS in PT symmetric system. Here I'd like to mention that in unitary case, that is for Hermitian system, the maximum violation of standard LGI is 1.5, and so even if we increase the dimension of system, then the violation can't be increased. But here we will see that the maximum violation of standard LGI achieves its algebraic maximum at the exceptional point. So for that, so this is the significance of this PT symmetric system in context of standard LGI. Even at in the PT symmetric field, the maximum violation is 2.54, which is much more higher than the Hermitian case. So for that, we choose observable M as sigma y and initial state as maximally mixed state, and this state evolves according to the equation 6 that we have discussed, and the two-time correlation can be computed using this formula. So in this scenario, we can get the expression of standard LGS, and we choose a particular WLGI for these values of M1, M2, and N3. So this is the this is the expression of WLGI, and quantum expression of standard LGI and WLGI comes to very lengthy, so I didn't put it here. But if we plot this standard LGI with respect to alpha and tau, then we can see that at alpha 1, that is at the exceptional point, the standard LGI reaches its algebraic maximum, that is 3, and WLGI is also reaches its algebraic maximum 1 at the exceptional point. Here I'd like to mention that there were two results last year that shows that this standard LGI reaches up to the algebraic maximum in different non-Hermitian system, but they somehow didn't discuss. So what is the reason for this? Here we provide a complete picture that at exceptional point, the coherence reaches up to and to the maximum value, and as a consequence, the algebraic maximum of LGS can be achieved. So now I come to my conclusion. We probe inequivalent form of LGIs in subatomic system with neutrino and meson system, and these inequalities exhibit maximum quantum violation around the energies corresponding to the maximum neutrino flux. And another interesting feature is the decoherence is observed to reduce the degree of violation for meson system and hence non-classical nature of the system. And we studied LGIs in PT symmetric system, and coherence is found to be maximum at exceptional point. And as a consequence, the standard LGIs and WLGIs achieve their respective algebraic maximum. So thank you for your attention. And if there is any question, then I'd like to answer those.
Yes, ma'am, there are two questions.
Yes.
The first question is, in the first assumption, you wrote macroscopic systems.
Yes.
So what does this macroscopic means?
It means the large mass, large size, high quantum number, high dimensional system. So up to this, and as I explained in this experimental thing, this macroscopic quantum coherence is observed in this C16 molecules and this.
Okay. So, and ma'am, another question is, why non-Hermitian Hamiltonian, which are PT symmetric, violate the Legit-Kirk inequality?
Could you repeat the question?
Why non-Hermitian Hamiltonian, which are PT symmetric, violate the Legit-Kirk inequality?
So if we take Hermitian system also, then also we get the violation, but it is not the algebraic maximum. And this non-Hermitian system, that is different. It is shown in the different work that is that algebraic maximum is achieved in non-Hermitian system, and PT symmetric is one of the non-Hermitian system. So here also we get the violation, but the reason of violation is the in this scenario is the this coherence is maximum at the exceptional point.
And ma'am, what is the mathematical cause behind it? Can we look something from eigenvalues perspectives?
Eigenvalues perspective means I didn't get the question. Which are you talking about, this PT symmetric system?
Ma'am, this question is in the chat box.
And I think this question is not complete.
Yes, ma'am, it is for PT symmetric systems.
Okay. Eigenvalue perspective means I will think about it. Okay.
Okay, ma'am. So, thank you, ma'am.
I think there is a question from YouTube.
Yes.
So Shashank Gupta is asking, is all inequivalent form of Wigner form of LGI are stronger than the standard form of LGI?
Yes, all Wigner form of LGS are stronger than the standard LGS. This, but yes, but here in neutrino system, but it depends on the measurement setting, that which out of this 24 Wigner form of LGS, which inequality is standard. So it depends on our measurement setting. So for this neutrino experiment, we can see that this Wigner or CH form of LGH, this CH LGH is this is relevant for this value of M1, M2, and M3. So out of these 24, these 24 are stronger than the standard LGH, but we for particular setting, this one can them the stronger than that. So so we will have to choose this state and observable in that way. So it depends on the measurement setting, but they are in general stronger than the standard LGs.
Thank you. Maybe we can, Anu, we can maybe go to the next talk.
Okay,
We
sir.
thank the current speaker. And we
Thank
go
you,
to-
ma'am, for your nice presentation. Our next speaker is Debashri Das from Bose Institute, Kolkata.
Before we move to Devashi can start sharing the screen. Anu, can I just make one announcement?
Yes, ma'am.
Yeah. So Naina Das, are you here? Naina?
Yes, ma'am. I'm here.
You know that you will be chairing sessions from 11 o'clock.
Hello.
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 Naina, you are chairing a sessions from 11 o'clock, right?
Yeah.
Yeah. Okay. Just to tell you, now you understand how to go. You just give a reminder to the speaker, maybe 5 minutes before, and the time is 25 minutes plus 5 minutes for discussion. And everybody is writing question in chat box. You have to read, and also the YouTube questions will be put by our moderator, and so you can just read that and ask the question. Okay.
Okay, ma'am.
Okay. So sorry. Now, Anu, you can. Devoshi can start.
Is the screen visible?
Yes, it is visible. It is.
Okay. Am I audible? Yeah. Okay. Good morning, everyone. First of all, I want to thank the organizers for giving me this platform to present my work. The topic of my today's talk is fidelity deviation in quantum teleportation with a 2-qubit state. Though quantum teleportation is a fundamental protocol in quantum information theory, and it has been studied extensively in various literature, but the concept of fidelity deviation in quantum teleportation is less explored. And in this talk, I will try to discuss on this concept. This talk will be based on these two papers, which are done in collaboration with Arkoprabha Ghoshal from Bose Institute, Saptarshi Roy from HRI, and Professor Somshubra Bandyopadhyay from Bose Institute. So I will start by discussing what is teleportation. Teleportation implies transferring of matter or energy from one point to another point without traversing the physical space between them. And it has been a common subject in science fiction literature. The natural question which arises, can teleportation be achieved in reality? And the answer is yes, we can do it with the help of quantum mechanics. So more formally, quantum teleportation is a fundamental protocol for transmitting quantum information using shared entanglement and LOCC. LOCC means local operations and classical communication. And quantum teleportation allows transferring of quantum states which are unknown to the sender over quantum channels without physical transmission of the quantum systems. So the quantum states which are being teleported are unknown to the sender. This is one important aspect. And this transfer of quantum state is possible even without any physical transmission of the quantum system. This is another important aspect. And Quantum teleportation can be viewed as an instance of quantum state transfer. In the scenario of quantum teleportation, two specially separated parties, say Alice and Bob, share some entangled channel, which is denoted by rho. Here, the two blue circles are denote the entangled channel, and Alice tries to teleport the state psi to Bob. Here, psi is the input state of the teleportation protocol, and this input state is unknown to Alice. In order to realize this teleportation protocol, Alice and Bob perform some local operation along with some classical communication, after which this is the output state of quantum teleportation. The final state of Bob is the output state of quantum teleportation. In case of perfect quantum teleportation, this output state is exactly equal to this input state. But in reality, one may not achieve perfect quantum teleportation. In that case, this output state may not be exactly equal to this input state. And in that case, the efficacy of the teleportation protocol will be denoted by the closeness between the output state and the input state. So the standard figure of merit for quantum teleportation is average fidelity, which is the fidelity between an input and output pair, and the average is taken over all possible input states. The average fidelity is 1 if and only if the entangled channel rho is maximally entangled. And in practice, one cannot expect maximally entangled channel. The available channels are noisy. That is why the average fidelity will be less than 1. And the maximal average fidelity or maximal fidelity is defined as the maximal average fidelity that can be obtained within the standard protocol and local unitary strategies. Here, standard protocol means the protocol that was depicted in the seminal paper by Charles Bennett. So, in order to, one can compute the average fidelity, this average fidelity under standard protocol, then one can maximize this average fidelity over local unitaries in order to get this maximal average fidelity. Any protocol that achieves this maximal average fidelity is said to be optimal. And a 2-qubit state rho is useful for quantum teleportation if and only if the maximum average fidelity is greater than 2/3. Because 2/3 is the maximum average fidelity that can be obtained in any classical protocol. With the help of classical protocol, one cannot exceed maximal average fidelity above 2/3. So whenever the maximal average fidelity is above 2/3, we can surely say that the teleportation is quantum. And maximal average fidelity is equal to 1 if and only if the shared 2-qubit state is maximally entangled. For any arbitrary 2-qubit state, the exact computable expressions for maximal average fidelity is known. Next, I want to introduce some notations and definition for which will be useful in my next slides. In Hilbert-Schmidt representation, any 2-qubit density matrix rho can be written in this form. Here, capital R and capital S are local vectors, and this coefficient Tij form a real 3×3 matrix, which is known as the correlation matrix. This correlation matrix will play an important role in this discussion. Now, suppose this small t11, t22, t33 are the eigenvalues of the correlation matrix of the of rho. Now, one can transform rho into this form under local unitary transformation, where the correlation matrix becomes diagonal. This transformed state is defined as the canonical form of rho. And there is a significance of this canonical form in the context of maximal fidelity. The maximal fidelity of any the maximal average fidelity of any 2-qubit density matrix rho is nothing but the average fidelity of its canonical form. So in practice, one can achieve the optimal protocol. Optimal protocol means which maximize the average fidelity in this way. Alice and Bob first apply local unitary operation to transform any 2-qubit density matrix into its canonical form. And then the canonical density matrix is used for quantum teleportation following the standard protocol proposed by Bennett. And the maximal expressions of maximal fidelity in quantum teleportation with 2-qubit states are known, and these are summarized in this table. When determinant of the correlation matrix is greater than 0 or equal to 0, the maximum average fidelity is always less than or equal to 2/3. On the other hand, when the determinant of the correlation matrix is less than 0, the average maximal average fidelity will be greater than 2/3 if and only if this condition is satisfied. So all useful 2-qubit states, useful means the 2-qubit states giving maximal average fidelity greater than 2/3. All useful 2-qubit states for quantum teleportation have the property determinant of correlation matrix less than 0. But the converse is not true in general. And from this table, it is clear that in order to theoretically calculate the maximal average fidelity, one need not find out the optimal protocol, one need not find out the canonical form, one just need to know the eigenvalues of the correlation matrix in order to compute these expressions. However, in reality, these optimal values are realized with the canonical form. But for analytical calculation, one need not find out the canonical form. So far, all the discussions of quantum teleportation was based on maximum average fidelity. But maximal average fidelity alone is not sufficient to fully characterize quantum teleportation. This is because, in general, there exist fluctuations in fidelity over the input states, either due to the imperfections in experiments or even as a property inherent to the resource states. In general, whenever the entangled channel is not maximally entangled, different input states will be teleported with different fidelities. And the average fidelity does not give any idea on this distribution of fidelity values over the input states. That is why we need some measure to quantify the fluctuation in fidelity, if any, over the input states. And one such measure is fidelity deviation, which is the standard deviation of fidelity over all input states. It is defined in this way. It is a measure of the spread of fidelity values around the average. And it is 0 if and only if all input states are teleported with same fidelity. And that fidelity is equal to the average fidelity. Now, since the maximal fidelity is realized with the canonical density matrix, we accordingly define the fidelity deviation in the optimal protocol like this. This is the fidelity deviation in the of the density matrix rho in the optimal protocol, which is nothing but the fidelity deviation of its canonical form. Now, the optimal protocol maximizes the average fidelity, but it may not minimize the fidelity deviation. In general, any strategy that maximizes average fidelity may not minimize fidelity deviation and vice versa. Hence, in general, this fidelity deviation in the optimal protocol is not the same as the minimum of fidelity deviation over all local unitary strategies. But since our primary motivation in quantum teleportation is to maximize average fidelity, that is why fidelity deviation is studied in the protocol which maximizes average fidelity. However, there exist states where the fidelity deviation in the optimal protocol is 0, and for such states, the optimal protocol indeed minimizes the fidelity deviation. And in our paper, we have explicitly derived the expression for fidelity deviation in the optimal protocol with a 2-qubit states. These are summarized in this table. Here also, in order to calculate this expression, one only need to find out the eigenvalues of the correlation matrix. One don't need to find out the canonical form or the optimal protocol. But this, in reality, this fidelity deviation in the optimal protocol is realized with the canonical form. Next, I will introduce the universality condition. The universality condition implies that the fidelity deviation in the optimal protocol is 0. That means all input states are teleported equally well. As discussed, as I have mentioned earlier, a 2-qubit state is useful for quantum teleportation if and only if this condition is satisfied. On the other hand, a 2-qubit state which is useful for quantum teleportation, that means with determinant of the correlation matrix, with negative determinant of correlation matrix, is universal or dispersion free for quantum teleportation if and only if this condition is satisfied. Combining these two conditions, we can state that a 2-qubit state rho is useful as well as universal for quantum teleportation if and only if these conditions is satisfied. That is when the modulus of the eigenvalues of the correlation matrix are equal to each other, and individually each of them is greater than 1/3. Next, I will discuss an important result. Let S be the set of all 2-qubit density matrices with maximal fidelity F, with some where F is fixed and it is greater than 2/3. That means we are considering only those 2-qubit states that are useful for quantum teleportation. Then it can be shown that there always exist states within this set which are universal. That means which satisfies this property. And for a given maximal fidelity, the most desirable states are those that are universal. Because when you are given an entangled channel and you know that the entangled channel is useful, you will be sure that all input states will be teleported with the equal fidelity, and that fidelity value will be equal to the average fidelity. But if the entangled channel is not universal, then different input states will be teleported with different fidelities. And in practical scenario, when you deal with some finite number of input states, you will not know, in case of non-universal quantum channel, with which fidelity that particular input states will be teleported. But if the entangled channel is universal, then that problem will not appear, because in that case, you know that all input states will be teleported equally well. So this is the significance of universal states, universal quantum channels. Next, I will discuss fidelity deviation for some well-known class of 2-qubit states. Let us start with 2-qubit pure entangled states, which is of this form. The maximal fidelity is always greater than 2/3. That means these states are always useful for quantum teleportation as long as they are entangled. And the fidelity deviation in the optimal protocol is 0 if and only if the state is maximally entangled. That means within the class of pure entangled 2-qubit states, maximally entangled states are only universal states. Next, I will discuss the Bell diagonal mixed states, which can be written in this form. And the maximal fidelity is greater than 2/3 whenever the state is entangled. The fidelity deviation for rank 4 class of Bell diagonal mixed states is 0 if and whenever the state is Warner state. On the other hand, for rank 3 and rank 2 Bell diagonal mixed states, the fidelity deviation is always non-zero. That means Warner states are the only universal states within Bell diagonal mixed states. There exists some non-Bell diagonal mixed states, which are also universal. This rank 3 states is one such state, which is universal. Another example is this rank 4 states, which is universal non-Warner mixed states. So the ordered pair, maximal average fidelity and fidelity deviation, contains all the necessary information we need to characterize quantum teleportation with a 2-qubit state. And fidelity deviation can serve as a filter to select the best possible resource states from a set of states having the same maximal fidelity. Whenever you are given, suppose you are given a set of states, a set of quantum channels, all of them have the same maximal average fidelity, then the best possible resource states within this state will be that state which have the minimum value of fidelity deviation, because in that case most number of the input states will be teleported with fidelity approximately equal to the average fidelity. Now suppose you are given a entangled channel which has average fidelity greater than 2/3 plus but close to 2/3. Now suppose that the state entangled channel is not universal. Then in that case, some input states will be teleported with fidelity less than 2/3 because that state is entangled channel is not universal. So even though the average fidelity is greater than 2/3, some input state will be teleported with fidelity less than 2/3. But if the entangled channel is universal, that means with fidelity deviation 0, then such problem will not appear. All input states will be teleported equally well. And with the help, with using the concept of fidelity deviation, we have defined optimal states for quantum teleportation. The optimal states are defined as those states that, for a given value of the state property under consideration, achieve the largest maximum fidelity and also exhibit 0 fidelity deviation in the optimal protocol. And we have addressed this question: which 2-qubit states are optimal for quantum teleportation for a given value of some state property? The state properties that we consider are purity, Bell non-locality, and entanglement. And in our paper, we have completely characterized such these optimal states for quantum teleportation. But I am not going into these details. So entanglement, Bell non-locality, purity, these are resources in quantum information processing task. In practical situations, one cannot expect that the entangled channel is maximally entangled, or the entangled channel is maximally non-local or pure. That means in practical situation, the availability of these resources are limited. Hence, one should focus on the best performing quantum states for quantum teleportation when the entanglement or Bell non-locality or purity of the entangled channel is limited. And our work addresses this question within the set of 2-qubit states. And finally, our characterization of resource states using fidelity deviation moves us closer to addressing issues during practical implementations of quantum teleportation. In case of practical implementation, one will not have all possible input states, rather some finite set of input states. And in that case, if the fidelity deviation of the entangled channel is not 0, then one will not know what will be the fidelities of that particular input states. In that case, vanishing fidelity deviation will play an important role. That is the significance of fidelity deviation. So thank you. And these are the references that are useful for this work.
So there is a question from Aditi Sende.
Yeah.
Isn't the teleportation fidelity that you mentioned via TIJ is when you opt for Bell measurement based teleportation? That is standard teleportation.
Yes, yes. 1 minute. The expressions are that are derived. I have mentioned that first local unitary operation is applied to transform any density matrix to its canonical form. Then that canonical form is used for quantum teleportation using following the standard protocol that was proposed by Bennett. So this formula is under that first unit standard local unitary transformation to transform any density matrix to its canonical form, and then by following the standard protocol. That means Bell measurement, classical communication of the result, and then local unitary transformation by Bob. Okay.
Hello, Anu. Are you? Hello? Hello, can you hear me?
Yes, ma'am. Yes, ma'am. There is another question. How do you define teleportation fidelity in case of mixed states?
Teleportation fidelity is mixed state means this is for any entangled channel.
No, I think he is saying that mixed state to be teleported. So
okay.
You have a row to be teleported, then how will you define?
Actually, the mixedness of the input state comes from the fact that comes from the subjective ignorance of the input state, and this subjective ignorance is already incorporated while we are taking the average over integration over all possible input states. That's why one need not consider mixed input states, because the mixedness concept comes from subjective ignorance. One does not know which particular input state is being teleported, and that concept is already incorporated. That particular concept is already incorporated while taking the average over all possible input states. So we don't need to consider mixed input states.
I just want to add, Devashi.
Yeah.
I think that you can consider in principle that you have to, instead of fidelity here, because just psi, you have calculated psi rho psi, right?
Right.
Then you average over psi, like sine theta d phi, and averaging.
Right.
So one can consider mixed state as the input as well, but then you have to consider another distance-based measure,
Right.
like P of say ρ1, ρ2. That will be the state. ρ2 will be the output, and ρ in can be the input. And any
Yes.
distance measure can be taken. I mean, whether it can be a distance measure according to some norm one has to
Yeah.
take. That
Right.
you can always define. I mean, there is
Yes.
no.
Yes. But this definition is
Yeah.
applicable when the input state is pure.
Yeah.
Yeah.
So I think, Anu, you have missed one question from Kapil that does bound entangled states. Can you?
Yes, ma'am. There's one more question. Does
Yeah.
bound and tangled states also exhibit the Ullmann fidelity deviation?
Actually, this in the present work, we constrained ourselves to 2-qubit state. In 2-qubit state, there is no bound entangled state exists. But the concept of fidelity deviation can be applied to any dimensional entangled channel, and whatever it may be the bound entangled channel. But the present work is for only 2-qubit states, and here no bound entangled state exists. So for higher dimension, what will be the features of fidelity deviation in case of bound entangled channel, that can be studied. But in our present work, we have not studied it.
One thing is that we know that the bound entangled states are not useful for teleportation. So I don't know
Yeah.
whether there is any point of fidelity deviation, because we know that the bound entangled states are not useful
Not useful.
for teleportation.
No, what I am saying that I have we have calculated, but
Yeah.
it will not be significant.
Yeah, it's for 2-qubit, that I understand, but I mean,
Yeah,
because the fidelity is always less than 2/3, so there is no point of calculating deviation.
right. But it can be defined, but it will not be significant because
So Kopil wrote that yes, it's true that the bound entangled state can help to increase the fidelity of quantum teleportation because of this activation paper of Horowitz. But okay, we are talking about the shared state, whether it is bound entangled. In that case, we calculate fidelity or fidelity deviation. What I want to say there, it may not be useful, but for activation, it is probably useful. That we know already.
Yeah. Right.
Okay, so there is another question from Shiladitya. So Anu can tell you. Hello, Anu.
There is another question from Shiladitya Mal. Filter based on which order of deviation is best if one consider higher order deviation than just dispersion?
I cannot get the question. Can I see the question? Then it will
You
be.
can see in the chat box. Can you see the chat box?
Yeah. Filter based on which order of deviation is best if one consider higher order deviation than just dispersion. Okay. I think Shiladitya is telling about the definition of the fidelity deviation that we have taken as standard deviation. So if one takes some other measure of fluctuation, then it can be taken, but the feature filter based on which order of deviation, we cannot say which order of deviation is which type of definition of deviation will be best to capture the distribution of fidelity values around the average. Different types of definition can be taken, and comparison can be done, but I don't know which will be the best.
Okay, sir. So thank you for your informative presentation.
Thank you.
So our next speaker is Siman Raj Sadana from Raman Research Institute, Bangalore.
Hello.
Yes, sir.
Yeah, am I audible?
Yes, sir, you are audible.
Yeah, I'll share my screen. Is my screen visible now?
Yes, sir.
Okay. Hello, everyone. I am Siman Raj from Raman Research Institute. And I thank for the opportunity to speak at this event. So the topic of my presentation is hunger mantle effect with classical light. And the publication which actually discusses this is right there at the bottom of the screen. Here is the outline of my talk. First, I will discuss what the hunger mantle effect is, and I'm sure that the audience is aware of that effect, but I'll just introduce it briefly for the purpose of refreshing the idea, and then I will also discuss the semi-classical theory of photoelectric effects. And the idea behind discussing these two topics is to see if there are semi-classical explanations of hunger mantle effect. So the thing is that the hunger mantle effect is actually thought to be a purely like a signature of the photonic nature of light. However, using the semi-classical theory of Sudarshan, Mantle, and Wolf, we can actually see that there are semi-classical explanations of hunger mantle effect, and that in fact we can simulate the hunger mantle effect using beams of classical light. However, by using the wave particle, by using the wave particle complementarity, we can actually distinguish between the hunger mantle effect, which is simulated using the classical light, and the hunger mantle effect, which is the actual quantum phenomenon. So let's start with the hunger mantle effect. That's a very simple concept. Say we have a 50-50 beam splitter, and we have two indistinguishable. Yes.
Shivan, can you come a bit close to the mic because you know your voice is kind of varying.
Okay.
Yeah.
Okay. Sure.
Yeah. Now it's fine. Yeah.
Yeah. Okay.
Okay. Yeah.
Yeah. So let me resume so discussing the two photon interference, which is, so let's say we have a 50-50 beam splitter, and we have two input photons which are identical and indistinguishable. So now intuitively, we would think that there are four possibilities of the outcomes. Is that either both are reflected, both are transmitted, or both exit from or both the photons exit from one of the two ports. However, if you apply the mathematics of quantum mechanics, you see that the reflected and the so 1-1 terms, the 1-1 terms actually disappear, the amplitudes disappear. So only the 0-2 and 2-0 terms are the ones that prevail, which means, in other words, that you will never see a simultaneous detection of a photon at the two detectors which are placed at the output of the beam splitter. So this is the hunger mantle effect. Now, here specifically so here specifically I have shown the scenario where the two photons are indistinguishable. But what about if the photons are distinguishable? So let's say that we introduce a time delay between the two photons and see how the probability of detecting two simultaneous photons at the output behaves. So there is this famous coincidence plot, which shows that if the time delay is much larger than the overlap between the wave functions of the two photons, then you see that you have some coincidence probability. And then as the indistinguishability increases, or the distinguishability decreases as the time delay between the two photons decreases, it drops to 0. So there is 100% drop in the coincidence probability. So that is the Hongo-Mandel effect. And it has been, so now what are the importance of this effect? So the first importance is that it's considered to be a very important signature of the quantum nature of light, because two-photon interference, because the folklore is that no classical or semi-classical theories can actually predict so semi-classical and classical theories predict a dip of 50%, right? And not beyond that. So this Hongo-Mandel effect is considered to be a signature of the quantum nature of light. And there are other applications of the Hongo-Mandel effect. For example, the original seminal paper of Hongo and Mandel, they actually use this effect to measure time differences between between two photons. If you remember that the name of the photon, the name of the paper was measurement of sub-picosecond times. So Hongo-Mandel effect can be used to measure stuff. And the other important application is the production of noon states, which is actually useful for many information. Yes, it's used for many information protocols. And then one more application of that effect is that it can be used to verify and quantify optical interferometers. So if you want to find out the unitary operator corresponding to an interferometer, then you want to then it has been shown that you only need to measure the single photon interferences and the two photon interferences. So this is the Hongo-Mandel effect. Now let's move to the semi-classical theory of photoelectric effect. So Mendel, Sudarshan, and Wolf, they actually presented a semi-classical theory of photoelectric effect, in which they said that, okay, let's say that the light is a classical field, but the detector is the quantum state, and photoelectric effect is the effect when the light actually causes a transition from the like the transition of an electron from the bound states to the free continuum states, right? So here is a light beam that actually falls upon a quantum state, and there are fluctuations in the light. So for example, here the fluctuation is in the phase. So the phase fluctuates. And using the first order perturbation theory, they had shown that the probability of this ejection is proportional to the average of the integrated intensity of the light falling upon the state. Now, this is assuming that the frequency of the light is above the threshold for that state, so that the transition can take place. But however, the probability is proportional to the average intensity. Now, this is also intuitive, because we have always been saying that the number of photons is proportional to the average intensity of the beam. So but if you look at it from the point of view of photoelectric effect, the number of photons is actually equal to the number of excitations. So, and the probability of excitation is proportional to the average intensity. So those statements are equivalent. Now, this was a single beam so this was a single beam scenario. Now let's consider that we have two sources and two detectors, right? And there is some fluctuation in source one, and there is some fluctuation in source two. Now, okay, there are specific scenarios in which there will be no fluctuation. In that case, the average is a constant. So we will ignore that case. We will just deal with the general case, because the special case of no fluctuations is simply trivial. So let's say that the source one has a fluctuation and source two has fluctuation. Now we want to know what is the probability that the detection will happen at R1 at T1 and at R2 at T2. And in the same paper, they showed that this probability is proportional to the average over the fluctuations of the intensity of the source 1 and the intensity of source 2. So this is sort of a cross correlation of the two beams. It has to be done, and then usually it's so it's also normalized over the individual intensities. So now, okay, so now this can be viewed in actually two ways. First you can the first way in which you can view it is that the fluctuation, the relative, okay, so the correlations of the fluctuations in the beams will decide the probability of the excitations and also the coincidence probability, because if we put T1 equals T2, then it's the, yeah, so if T1 is equal to T2, then it's simply the coincidence probability. So from the coincidence probability, we can actually find out the correlation between the sources, or the other way around, from the correlation between the sources, we can find out the probability of the fluctuation. So let's apply this formula using classical light to a scenario in which two beams are input on a beam splitter. So let's say we have a 50-50 beam splitter, and then we have two input pulses, which are represented by equations here. So these equations are only for only for completeness, but the shape of the pulses are enough to understand the whole problem. However, there are two parameters in the equation of these pulses. So one is the phase, the relative phase between the two pulses, and also the relative time delay between the two pulses. So we will play around with these parameters and see what the outcome of the correlation function is. So the output after a 50-50 beam splitter is like well known, it's easy. And then using this output, we find out the correlation as a function of the time delay, which is here, right? And the definition of I of tau is here. It's the I of tau is the overlap between the two pulses. Now, as you will see that this probability is not only a function of the time delay, but also a function of the probability distribution of the fluctuation. So let's say that phi is the phase and it fluctuates with a probability distribution P of phi. I'm sorry for repeating the notation, which may be confusing, but the P here is different from the P here. Here P is the fluctuation of the phase between the two pulses. So it's not only a function of the time difference between the two pulses, but also the probability distribution of the fluctuation of the phi. So now let's consider a very trivial scenario in which there is no control over the phase between the two pulses and it's completely randomized between 0 and 2 pi. In that case, if we plot this C of tau, you will see that there is a 50% drop in the, so this is, yeah, so this is at 0.5. So it drops to 50%. So if you see that there, okay, so if the phase between the two pulses are completely randomized, then we have a 50% drop. And this is, yeah, and so this result is where the folklore actually comes from, that the semi-classical theories can only predict up to 50% dip. It can only be less than that. And it will be less if the distinguishability or identicality of the two photons reduce, right? So then, like if the two pulses are not exactly identical, this dip will reduce. But in the case of perfect identicality, if that is a word, identicality, the drop will be exactly 50% and it won't be beyond that. So, but however, as we see that it's also a function of the probability distribution of the fluctuation, how about trying out other fluctuations? For example, there are other fluctuations which we can employ. However, we will put a condition on those fluctuations. So the condition on the fluctuation is that it should erase the second order interference. Now by second order interference, I mean field, and not the intensity. Intensity, I will call the fourth order interference. So it must erase this So the fluctuation should be such that it should erase the second order interference, so that there should be no doubt that this dip is actually not due to just some adding or subtraction of the fields. Because the second order interference has been erased. So this is so here is the condition it should obey. And then once the second order interference is erased, you like the fourth order interference will actually reveal itself. So here is an example where we saw that if you have no control over the phase, then we have 50-50. And let's say we have another probability, like another fluctuation in which it shows a 50% dip. And the thing with this fluctuation is that it obeys this equation where it erases the second order interference. Now the question is, are there fluctuations which erase the second order interference but show a dip in the fourth order interference which is beyond 50%? And the answer to that question is actually yes. So let's say we take a fluctuation of this type where the phase fluctuates between 0 and pi and it's completely random, right? Now it's easily verifiable that this probability distribution erases the second order interference. So whatever the effect is at the whatever the output correlation is, it's not due to simply the addition and subtraction of the fields, because that has been erased. But with this probability distribution, we see that the dip is actually 100%, which actually which is expected out of a Hongo-Mantle effect. And there are other probability distributions for which the dip is between 50% and 100%. But here I'm showing only one specific case where the dip is 100%. So Hongo-Mantle effect can be simulated using beams of classical light. Now the question is, so what, right? What is the importance of this effect? And if Hongo-Mantle effect is actually simulatable using classical light, how will you distinguish between the classically simulated HRI effect and the quantum? So first, I will address this problem with the help of a thought experiment, right? So it's an operational attack on the problem. Let's say we have two parties, Alice and Bob, where Alice has a source and Bob has two detectors. Now Bob asks Alice to send him 2 photons, right? And Alice says, okay, I will do that. But secretly, Alice has a classical source. She does not even have a source of photons. She has let's say CW source or something, right? But she does not reveal that to Bob. But she actually says, she falsely promises Bob that I will send 2 photons to you. But Bob says, okay, I am a bit, okay, so I will do some tests on your photons to see if you have actually sent me photons. And Alice asks, okay, so tell me the test which you will do. Bob says, I will do the first test, which is the HRM effect. I will actually look for the HRM effect because it's a signature of 2 photons. And because photonic states also exist in superposition states, if I pass them through a Mach-Zehnder interferometer, they should also exhibit interference. So here are the 2 tests that will be done by Bob, but Bob will actually reveal the test. So the thing is, if Bob reveals the test, then Alice is very clever. She knows that if he does an HOM test, right, then Alice knows that if she chooses the fluctuation of her beams to be this, which is 0 and pi, right, then actually she will pass test 1, right? So Bob will think, okay, it passes the HOM test. And then subsequently, if Bob says that now I will do the interference test, then Alice secretly changes the setting to a uniform distribution of phi. And then Bob declares that, okay, Alice has actually sent me photons because it has passed test 1 and test 2. And so Alice, although she had a classical source, she fooled Bob into thinking that she has a quantum source. So that is a problem because Bob was not able to distinguish between a classically simulated HM and an actual HM. So what is the solution to this problem? So Bob actually thinks for a bit and then comes up with a solution. He says, okay, so Alice, if Alice actually knows the test I'm doing, she can change the settings. However, if I do not reveal the test, then she won't be able to fool me because then she will not know the setting she has to use. On the other hand, if Alice actually had a quantum source, right? So then she wouldn't have to change any setting because photons will pass both the test because of the because photons exhibit the duality of a wave and particle. So it can pass both the test without having to change any source setting. So Bob says, okay, I will hide the test now. And now you send me the photons. So now Alice is confused. So if Alice has a classical source, she does not know the probability distribution or the fluctuation setting that she has to use. On the other hand, if Alice had a quantum source, she would have no worries because she would know that she would pass all the tests. So this is the role of complementarity. So Hongo-Mantle effect, like on its own, is not enough to actually conclude that Alice has a quantum source. You have to do a wave particle like duality test to actually distinguish the HOM which is simulated classically and the HOM which is exhibited by photons. So this was the whole idea. And then we also did an experiment to we did an experiment to demonstrate this effect. So here is the brief outline of the experiment. The details are in the paper, but due to lack of time, I won't be able to go into the details of the integrity of the experiment. So we did the experiment with microwaves. So and the advantage of using microwaves is that we can actually hook it up to an AWG, which is an arbitrary waveform generator, and we can actually we can have a complete control over the relative phase over the phase of the two pulses. So that's an advantage of using the AWG with the microwave. And then we showed the HOM effect. So this plot, which I showed earlier also, is from the experiment that we had conducted. And then subsequently, we also conducted we also demonstrated the wave particle complementarity difference between the classical and the quantum. So we first did the classical experiment, and then we also had so my other collaborators in the paper, they also performed the quantum version of this experiment. And then instead of putting a phase shifter in the Mach Zehnder for the interference pattern, we actually put in a blocker. So we would compare two results, so one without the blocker and one with the blocker, and then we would see what is the change in the coincidence. And then if the classical and quantum are different, then the difference in the output of the correlation in the blocked and the unblocked case should be different for the classical and the quantum. And then indeed we saw that the ratio of the coincidence when it's blocked to that when it's unblocked is 50% in the classical case, and then it's 1/4 in the quantum case. And and I haven't shown it here, but these are the results which are actually also mathematically expected from the two scenarios. So so here was the experiment to demonstrate that. So with that, I will now summarize my talk. So the first thing was that the Hongo-Mantle effect is not a definitive test for a quantum source, because as I have shown that it can be simulated using a classical source, and you can fool the observer into thinking that it is a quantum source. And then the second important thing is that the semi-classical theories, although they are inadequate in they are inadequate in explaining everything, but they can, in some sense, explain the Hongo-Mantle effect. And yeah, and then the third point is that we need complementarity tests to actually distinguish between the classically simulated HRI effect and the quantum one. So with that, I conclude my talk. Thank you. If there are any questions, please post them. I'll also check the chat box. Hello.
Anu, are you there?
Yes, sir. Sir, there is a question from Ujjwal Sen. Is there an implication of your results for the result on so-called classical entanglement?
Okay, so that's a very nice question, because, and I also understand that the question comes from the fact that we have 0, 2, and 2, 0 type of states, and then we can actually apply these two. So at this moment, I haven't explored that problem yet, but even I have thought about it, and it seems that using semi-classical theories, we could actually attempt at looking at or analyzing the classical entanglement. But that's a very nice question, and I appreciate it. But at this moment, I haven't explored it to that extent as to answer the question yet. But thank you.
So there's another question from Shaladitya Mal. Does one can distinguish classical and quantum noise even if interference complementarity is not perfect?
Oh yes, so we had done the, okay. So the imperfections are always, for example, in our experiments also, you will see that there are error bars. So so there are noises, and then there are imperfections, and the dip is not 100% always. But however, you can still actually okay, so the difference between 0.5 and 0. Okay, so I'll show you the difference. Okay, so so you'll see that that there is a huge difference here, 50% and 25%. So this difference is actually enough so that even if there are small amounts of noises, we can actually have a very fairly clear idea of the classical and the quantum one. If the noise is too much, then the experiment is it has to be redesigned anyway. But for decent amount of noises, we can make clear distinctions between the classical and the quantum.
Okay, sir. So there's one more question from Aditi Sende.
Yeah.
Have you done wave particle duality experiment?
Yes. So this complementarity experiment. So okay, so there were two legs to it. Okay, so the first leg was to actually show the HOM effect, and we also had a quantum analog of that,
Can you sorry, Suman?
Yeah.
Yeah, Arindam, can you mute? There is some noise coming. Hello, Arindam. Yeah. So Shivan, can you continue? Sorry.
Yeah. Okay, so there were two legs to the experiment. First, we had to actually demonstrate the Hongo-Mantle effect using both the classical and quantum. So we did that, right? Now, after
Sir, in that experiment, what have you measured to check duality?
Yeah, so okay. So yeah, so okay, so I'll explain the experiment. So the first leg was to actually yeah. Okay, so the first question should be, how did we actually measure the Hongo-Mantle effect in the classical one in the first place? So how did we measure? So this dip is actually this correlation function. So I'll show you where was the correlation function. Okay, so we measured this correlation function for the classical one, and then for the quantum one, like I simply have to measure the number of clicks, and then we compared the correlation with the number of clicks, and then saw that actually both of them show 100% dip. So so here's the first step. So we show the Hongo Mantle effect using both. Now in the second leg, in which we have to show the wave particle duality. So what we do is we first where is it? Yeah. So we first actually set both the experiments, the classical and the quantum, at the HOM setting, so that both of them show the HOM setting. And now we extend the apparatus to make the arc center interferometer, right? Now in the arc center interferometer, we will again measure the number of clicks in the quantum case and the correlation function in the classical case. However, we will have we have two scenarios here. First, in which one of the arms of the MZI is blocked, and the other case in which it's unblocked. And then we measure the ratios of the outcomes for the two cases. And then we see that the ratio are starkly different, and mathematically we can show that this difference is expected from the quantum and classical. And plus, we can also show that this difference actually occurs from the fact that photons can actually exist in superposition states and show wave particle complementarity. On the other hand, the classical pulses fail to do that, and the outcome of that result is this difference.
So there's another question from YouTube.
Yeah.
Hansatanu Roy, what is the order of coherence time here?
The order of coherence time. Okay, so you will see the range of the time delays that we have taken here. So it's in it's about 6 milliseconds or so, like plus minus. So we have maintained the coherence time of each each of the classical pulse to be within, well within that range, -6 to 6. So for example, if this is if this is like 10 to the power -3, so we chose the coherence time to be about 10 to the -6 or something, so that we are well within the range over which we have the time delays.
Another question is from Nitika from YouTube. Is there some connection for the complementarity with non-locality to probe the classical versus quantum cases?
Yeah, so non-locality stuff again. So I think this is on the same lines as the as the questions asked by Ujjwal Sen. So these are the things that for example, the classical entanglement and the non-locality stuff. These are some things that I haven't explored yet. But these are interesting problems, and I'll definitely explore them. And maybe in the next talk, I'll be able to highlight these results. But for now, I don't have an answer to that. I'm really sorry.
So the last question is from Hansatanu Roy. Is there an analogous experiment for the HOM effect for gravitons?
Oh, I'm not aware of that. Like gravitons and all, I don't even know if I don't even know if an HOM effect has been shown for them, and I don't know if it's easy or doable or not. But yeah, but I would not make any comments on that. I just don't know.
Okay. Thank you, sir. It was a nice presentation.
Yeah, thank you.
Thank you for such an informative presentation.
Thank you.
Okay, so we also thank Kanu Kumari for chairing this first session today, the first morning sessions of UQ. It's very nice, Anu. Thank you very much.
Thank
So
you.
now probably we should ask request Naina Das to
Ma'am.
chair the next two talks. So mic is in your side now.
Okay. Thank you, ma'am. So the next speaker is Biholan Bhattacharya from SN Bose National Center of Basic Science, Kolkata. Are you here, Biholan?
Yes, I can hear you. Am I audible?
Yeah, you are audible.
Okay,
You can
so
start
yeah,
your screen.
let me share this. Is it visible?
Uh, Still not. I think it's coming. Yeah. It's now visible. You can start.
Okay. So can I start?
Yeah.
Okay. So very good morning to all. At first, I'd like to thank the organizers for giving me this platform to present one of our works here. So today, I'm going to talk on convex geometry of Markovian Lindblad dynamics and witnessing non-Markovianity. So this is a work is based on this is the title of the paper. I've written the same title of the talk with the paper. Hello.
Hello. Yeah.
Am I audible?
Yeah. Some mic was mic was on. Please mute all of you. Please mute the mics. Okay. Yeah, Biholan, please continue.
Okay, thank you, ma'am. So this talk is based on one of our recent work, that convex geometry of Markovian Lindblad dynamics and witnessing non-Markovianity. I've written the same title of the talk as our paper. So this is a reference, and this work was done with Dr. Shamodeb Bhattacharya. So let me start. So this is the plan of my talk. First, I'll try to give you a basic introduction to open quantum system, and then I'll try to motivate you for this problem. And for that, I'll require a few definitions to be addressed, and I'll talk about these definitions. And then I'll come to the non-Markovian witness part, mainly the existence of witness and the construction. And I'll show two types of construction of non-Markovian witness. And I'll illustrate these constructions, or rather this non-Markovian witness, with some qubit examples. And then I'll come to the case that qubit non-Markovianity can be detected using famous Bell states as well. And one of the most interesting part of this work is the geometry of Markovian operation. I will come to that the next half, and then I'll conclude. So this is basically the plan of my talk. So let me start. So in my introduction to the open quantum system, for the sake of completeness, I'll go the brief introduction to that. So what axioms of quantum theory tells us that if a quantum system is there, and if it is isolated from the environment, if it is a closed quantum system, then the axiom of quantum theory tells us that the dynamics of the system is governed by the unitary one. But in a practical scenario, this is not the case, because the quantum system is usually associated with some environment, and it readily interacts with the environment, and there are different kind of decoherence and dissipation kind of irreversible phenomena takes place. And as a consequence of which, the system actually loses its information from the system to the environment. So there's a one-way traffic, that the system loses information, the information goes from the system to the environment. And as a result, it actually goes to some non-equilibrium steady state. And this one-way flow of information is basically a consequence of Born-Markov approximation. And if the corresponding environment is very large, then it actually, in turn, it leads to the complete positive divisibility of the dynamics. I'll come to the technical details of complete positive divisibility later, but I'll explain later that what CP divisibility is. Now, the thing is that in all cases, that system environment coupling may not be weak. So in the beyond weak coupling limit, so we can have this CP divisibility may break down. And if this CP divisibility breaks down, then it may happen that information that that was a one-way traffic, that was from system, the information was going to the environment. That information can there may be a backflow of information from the environment to the system. So that is why it is called the backflow of information. That information may come from the environment to the system. So this backflow of information can be used in various quantum mechanical tasks. That is, it can be treated as a resource, like other resource like entanglement, coherence, or other thing we are familiar with the resource. So this backflow of information is also you can treat it as a resource. There are several works, you can check these references 6 and 7. So they have basically used, or they have treated this information backflow as a resource. So whenever some resource is there in our hand, so we can talk about, or we can think about two questions: that what is the best way to understand a resource? Obviously the concept of resource theory, because there are existing resource theory of entanglement, coherence, thermodynamics, all these things. So obviously, as in backflow of information as a resource, if we can consider, then we can think that there is a possibility of resource theory of that. And the second question comes in our mind, that how to witness or how to detect this resource. This is also the same question that one asked in the entanglement theory as well. So we have actually addressed both the questions in two works, and for this talk I've actually focused on the second part, the second question, that how to witness or how to detect this particular resource. But also I will touch the first question as well, because I need to discuss a little bit about the resource theory of non-Markovianity that I have addressed, that we have addressed in a separate work. So this is basically the motivation, that we have the resource. Can we consider the resource theory of that, and also how to detect this resource? This is basically the primary motivation of this work. So some definitions are required. So let me go through one by one. So for the timing, in our discussion, we'll consider the finite dimensional Hilbert spaces only. Let us denote with an alphabet H, and this is a finite dimensional Hilbert space on the complex field of complex numbers. Let BH stands for the space of all operators on H, and for the finite dimensional, as we are considering finite dimensional cases, these all operators are bounded, and we can identify them as a matrices. So a linear map from BH to BH is called a positive map if it takes a positive cone of operators to the positive cone of operators. That is, it takes a positive element to a positive element of the codomain Hilbert codomain operator space. So it takes a positive element to the positive element. Now, as an extension, we can have a linear map to be k positive. K is some positive integer, k positive, if the map tensored with the identity map acting on the BCK. CK is a basically k-dimensional complex Hilbert space, and BCK is basically the space of all bounded operators on the CK-dimensional Hilbert space. So lambda, there's a map tensored with I, there's an identity map on BCK. If this map is positive, then we call the linear map to be k positive. And on a similar note, the map is called completely positive if the map lambda tensor IBCK is positive for all k belongs to natural numbers. For every positive integer, if it is positive, then we call the map to be completely positive. And another definition is the trace preservation condition. That is, a map is called trace preserving if the initial trace of the operator is same as the trace we found or find after the application of the map. That is, trace of lambda A is same as trace of A for all A in BH. These are some basic definitions. Okay, so complete positive and trace preserving maps are often considered as quantum channels, and quantum channels are very useful and important thing are in quantum information theory. Now we will consider a one parameter family of CP maps basically, and this parameter is basically some non-negative parameter. We can think it as physically as a time. So we consider a set of CP maps indexed with the time parameter. So this is a lambda t, as you can see, this is a lambda t, t is non-negative, and lambda t is CPTP. We call this set as a dynamical map, and this dynamical map actually gives us the notion of the dynamics. Now, a dynamical map, which is basically a set, is a family of map indexed with some time parameter. A dynamical map is said to be divisible if I can decompose the map lambda t as some operator, some linear map VTS times lambda s, where s is another time which is less than t. That is, we can think of that the dynamics that is that is there. We can think it as a part that it is. We are considering the dynamics from 0 to s, and then some s to t. This s to t part is governed by this VTS, and that is the total dynamics lambda t. So sometimes this VTS, which is a linear map on BH, is called the propagator of the dynamics. Now, if we put further restriction on this VTS, because we have considered VTS as simply a linear map on BH. If we consider further restriction on VTH, if we consider this to be a complete positive map, as I defined complete positivity earlier, if we take this VTS as a complete positive map, then this lambda t, this dynamical map, it becomes CP divisible, that I was talking in the introduction section. So CP divisibility is basically, it's a divisible dynamical map with VTS, the propagator, to be completely positive. Now, sometimes these CP divisible dynamics are considered as the quantum Markovian or memoryless dynamics. So this for the definition, it goes on, but now we can think about that we are considering the resource theory of non-Markovianity. So why we are considering the CP indivisibility, that the negation of the CP divisibility, as a figure of merit. So we can think it in this way, that we are considering information backflow as a resource, that the information that comes from environment to the system, this is our resource. And now CP indivisibility is necessary to have information backflow. So obviously we should, as a figure of merit, we should take something that actually gives. So obviously there may be some operations which are CP divisible but non-Markovian. But in hello, am I audible?
Yeah, you are audible.
Oh, okay, thank you. So there may exist some operations which are CP divisible but non-Markovian. But from a resource theoretic point of view, as they are CP divisible, we cannot have information backflow from them. So obviously we can exclude those kind of operations for the resource theoretic perspective. So that is why CP indivisibility is we can consider as a figure of merit. Now I'll briefly discuss the resource theory of non-Markovianity that we have addressed. And for that, we would like to say that we have restricted ourselves to a particular class of operations, and that particular class of operation we consider is that dynamical maps or the dynamics which have Lindblad coefficient or Lindblad form. Basically, this is the Lindblad equation. That's the equation of motion is given by this particular form, where gamma alpha are basically the Lindblad coefficients, and L alpha, these are the Lindblad operators, and gamma alpha, non-negativity of gamma alpha actually gives you the signature of the Markovianity, and if the dynamics is non-Markovian, then gamma alpha is negative. So this is a particular form we have considered. Now, since the CP divisibility is basically, it gives us a memorylessness, so obviously these should be the free operations, because in a resource theoretic perspective, one has to identify what are the free things, what are the free operations, or what are the free states in usual resource theory like entanglement. But one thing we should keep in our mind, that non-Markovianity is not a property of the state, it is a dynamical resource. So the resource theory of non-Markovianity will not be exactly same as what we do in entanglement or thermodynamics kind of thing. So this is a dynamical resource. So here we identify what are the free operations, basically. So free operations are basically the CP divisible Markovian operation. One important point is that there is a famous Choi-Milankovsky isomorphism, which actually translates everything into the language of map to the language of operators. It is very useful in various cases or various point of time. It actually translates everything to the language of operators. So we have also used this language here. So corresponding, we can consider the corresponding Choi matrix. There is a this particular map is applied on one part of the corresponding maximally entangled state, and we consider the operator Cm t plus epsilon to t. And this one point I should mention here, that t plus epsilon to t is basically the span of the dynamics we are considering, where epsilon is some positive quantity. But for the Markovian case, this Choi matrix is a very density matrix. So it has a Hermitian operator with trace norm 1. So for Markovian case, this is a very density matrix. And so in this way, we can consider about free states, because we are basically having some density matrix, we are having some states. In this way, we can consider free states, but since we are considering the dynamical resource, so free states is not that relevant in our discussion. So we identify what are the resourceful operations, and we identify what are the free operations, because identifying free operation will give us what are the resourceful operations. So in our case, in the resource theory of non-Markovianity, free operations are CP divisible operations. Now the question is, before going to the witness part, I have to show this theorem or proposition. There is a proposition, because okay, fine, we have considered the CP divisible operations as a resource free operations, but there was a result that Markovian operations, they do not form a convex set. Usually in our resource theory of entanglement or usual resource theory, okay, resource theory may not be convex, but it is this convexity is a nice property. This gives us some geometric notion. So there is one can ask that whether the corresponding resource theory is convex or not. So in general, Markovian operations do not form a convex set. There was a work by Toby Cubitt, M. Wolf, and also there was two work actually. Michael Wolf was in both the works. So there are evidences that Markovian operations do not form convex set. But what we can consider the dynamics to happen for a very small amount of time, that is t to t plus epsilon. That epsilon is in our hand, so we can take this epsilon as a limiting case. Epsilon tends to 0. But in this limit, if we consider the dynamics to happen within a very small interval, we can show that Markovian Choi states form a convex set. So we call it a small time interval approximation. So under small time interval approximation, Markovian Choi state actually forms a convex set, we have shown. This proof is not the rigorous proof, but we can talk about some sketch of the proof that we have considered. That we consider two Markovian operations, and also both of them has Hilbert coefficients, Hilbert generators. So considering epsilon to be very, very small, so we can take the expansion of the dynamical map up to first order, because for the second order onward, epsilon, since it is very small, so we can neglect those terms. So basically we have exploited the convexity of the Limbladian structure we can define the map lambda m t plus epsilon to t, which is basically the convex mixture of lambda 1m and lambda 2m. By exploiting the convexity argument of the Limbladian structure, we are having the convexity of the Markovian operations. But one thing again we have to keep in mind, we have considered the dynamics to happen for a very, very small amount of time. But under small time interval approximation, we are having this convexity. And moreover, we can show that this set, the Markovian operations under small time interval approximation, I shouldn't say this small time interval approximation is required here. Okay, for the time being, we are considering the small time interval case. So this set also forms a compact set. And since we are sitting inside the Euclidean space, we have the Heine-Borel theorem, that is a set is compact if it is closed and bounded. So the boundedness comes from the finite dimension, because we are sitting inside the finite dimensional case. So this all have the finite norms. So this will be bounded, and the closedness comes from the continuity of the trace norm. So in this way, we can show that this Fm epsilon, that the set of Markovian operations under small time interval approximation, it forms a compact set. Now we are having a convex set under small time interval approximation. We are having a compact set. So we can go further. We can have Crane-Milman theorem to establish that this FM epsilon is basically the convex hull of its extreme points. We can have this particular feature of convex and compact set. We have the Crane-Minvan theorem. Now, this actually gives us a platform to use geometric Hahn-Banach theorem to show the existence of non-Markovian witness, and that we have shown in the theorem two part. This is a non-Markovian Choi matrix can be separated from a Markovian Choi states by a hyperplane, and that is basically an application of the geometric Hahn-Banach theorem. So since we are considering a particular, say we are considering a non-Markovian Choi matrix, and this if the distance we consider from the FM epsilon, that is 0 if and only if the CNT, that is that particular non-Markovian dynamics, it is actually inside the topological closure of FM epsilon. But we have already shown that is the compact set, so the closure is the set itself. So clearly this is that the distance is strictly positive. It means that that particular Choi matrix CNT T plus epsilon to T, that actually is outside the FM epsilon set. And since a singleton set we can also always consider as a convex set, and we have already shown the convexity of FM epsilon under the small time interval approximation. So these two convexity along with the compactness of FM epsilon. Okay. So this singleton set as a convex set, and also the FM epsilon to be convex, we have shown under small time interval approximation, and along with the compactness, so we can always construct in principle a hyperplane that will separate these two objects. So this is the same idea that we do in the entanglement theory as well. So in this way we can show the existence of non-Markovian witness. And this is a schematic diagram you can think of. This is the lines that's basically the linear witnesses, and these green dots are basically, you can think it as a non-Markovian Choi matrices. And this is the FM epsilon, which is convex under small time interval approximation. It is not convex in general, but if we allow the dynamics to happen for a very small interval, in that case it can be shown that this is a convex set. So this is the kind of schematic diagram. So formally we come to the definition and construction part. The definition of the non-Markovian witness can be coined in this way, that it is a Hermitian operator, and the Hermitian operator is said to be a non-Markovian witness if it gives us the non-negative expectation value for all time and for all Choi matrices corresponding to that dynamics. And if there exists some time, some t, and some epsilon, that is some span of time, if we have some dynamics so that the expectation value is negative with that Hermitian observable or with that Hermitian operator, then we say that that Hermitian operator can be taken as a non-Markovian witness. This is a similar definition that we do in entanglement theory, because I am actually quoting every time that okay, we are going actually side by side with entanglement theory, because to show you the similarity of this theory with the theory of entanglement. So how to construct this non-Markovian witness? One thing we can have that this construction, since we are in a finite dimensional cases and these are all Hermitian operator, we are having the spectral decomposition of the operator. And this is kind of trivial construction, but still I would like to say that this is a, so we are having the spectral decomposition of the dynamic of the Choi matrix, and where this lambda I pi, this is summation of lambda I pi, where pi is the corresponding orthogonal projectors corresponding to the eigenvalue lambda I. So if the dynamics is CP divisible, then CQ T plus epsilon to T, that is the Choi matrix corresponding to this dynamical part, is a valid state for all T and epsilon. So these all have a non-negative eigenvalues, and hence the expectation is non-negative corresponding to that projector Pj. For all projector Pj, this will have the non-negative expectation value. But if the dynamics is non-Markovian, then they will possess at least one negative eigenvalue. So it will be detected by some of the projector, orthogonal projector, some j, at least one j, it will give us the negative expectation value. So thus we can say that orthogonal projectors actually serve as a witness for a non-Markovian operation. For a given non-dynamics, what we have to do, we have to take snapshots and we have to take cause we have to consider the projective measurements actually at the different temporal points on the during the evolution, and from that in principle it can be we can conclude about the nature of the dynamics, whether Markovian or non-Markovian. Okay, so these are some examples, some qubit examples. So this is the first one we have considered the defacing channel. This is a defacing in sigma z, in the z basis. And as you can see that if we consider the Choi matrix, this gives us the eigenvalue 0, 0, lambda t epsilon and 1 minus lambda t, gamma t epsilon, I'm sorry, gamma t epsilon. But the thing is that this epsilon is a time parameter. So it is on our hand. So we can have this 0, 0, we don't need to bother about, but this 1 minus gamma t times epsilon, this parameter, we can consider this to be positive because by tuning the epsilon parameter, we can take this as a non-negative thing. But what about this gamma t times epsilon? If gamma t times epsilon, this epsilon is a time, is always positive thing, but this gamma t, if it is negative, then it is always giving us the negative eigenvalue. And if it is non-negative, it is greater or equal to 0, then this always gives us the non-negative eigenvalue. But from 1 minus gamma t epsilon part, we cannot conclude actually. But so what I'm trying to say is this gamma t times epsilon is basically that particular eigenvalue whose eigenvector, whose corresponding eigenvector actually gives us or serves as a non-Markovian witness. And as you can see that this is the projector corresponding to this chi 0, 1, 0, 0 transposition is the corresponding eigenvector. We have to consider the projector chi to detect the non-Markovian. This is another example of qubit Pauli channel, and this is the Lindblad equation of the Pauli channel, where eigenvalues are basically this, as you can see. Check these eigenvalues: gamma x t epsilon, gamma y t epsilon, and gamma z t epsilon. So this, any of them, if it is negative, then it actually gives us the signature of non-Markovian. And if all of them are positive or at least non-negative, so we can think of this, the dynamics is Markovian. So basically the witness are respectively the corresponding projectors. So any one of them can serve as a projector, because we don't know that at which basis is basically it will give me the negative thing. One important point is that this particular dynamics, the dynamics of this depolarizing channel, is usually called in the literature that eternal non-Markovianity. Sometimes this non-Markovianity cannot be detected in various measures. So in this approach, we can detect the non-Markovianity of this kind of operations. This is one advantage we can see. And I'll also come to this example again with some other context that Bell state, using Bell state that I was talking about. Okay, so there is a second way of construction, the non-Markovian witness. That is, this construction depends basically some structural insight of the theory. That is the corresponding. For that, we need to go through some theorems first. That corresponding to any non-Markovian operation, there always exists a nearest Markovian operation. So given any non-Markovian dynamics, we can in principle have a nearest Markovian operation from the set Fm epsilon. Okay, but that finding that may be difficult, but there exists, in principle, there exists a nearest Markovian operation. And this is done by, actually we have defined a real valued function from Fm epsilon to R. So this function is based on the distance, and distance based function is always continuous, that we know. So any continuous function defined on a compact set is very powerful, that it has different properties. So what we can say that since this is a compact domain, it is a continuous function of the compact domain, so its infimum is there, it exists, and not only that, there is some point on the domain at which this infimum is achieved. And since this is a distance function, so as you can see, this is a distance function. So distance, the minimum distance is basically achieved with some particular Markovian operation, and that particular Markovian operation is the, we can say, the nearest Markovian operation corresponding to some non-Markovian dynamics. So in principle, we can have a nearest Markovian dynamics corresponding to a non-Markovian operation. Okay, now the question arises whether this nearest Markovian operation is unique or not. Obviously, this is not unique. This may not be unique. what we can say that in the proposition 2, the uniqueness criteria, that the nearest Markovian Choi state, the uniqueness criteria follows from this particular proposition, that if this expectation value, as you can see, this is as an expression, this is a little bit big. So if this expectation value is non-positive, it is less or equal to 0, then particular CM star, that was a point where infimum was achieved. That was a point what was the nearest Markovian Choi state. At that point is basically unique. So uniqueness comes from this particular criteria, and we like to emphasize here that the similar result holds in entanglement theory. We can have a nearest separable state, and also okay, so theorem 4 tells us that using this nearest Markovian Choi state, we can construct a non-Markovian witness. In principle, it may be hard to construct, but in principle, we can construct a non-Markovian witness exploiting this particularly nearest Markovian Choi state. And this is also same as entanglement theory. In case of entanglement theory, we can also have a nearest separable state for a given entangled state, and we can consider an entanglement witness exploiting this particular nearest separable state. Here also in theorem 4, we have shown that in principle, yes, ma'am.
You are minus 5 minutes.
Okay. Sorry, ma'am.
Okay, so I'm trying to wrap it up quickly. I think
okay.
Interfere Noina has already sent you the reminder in a chat box, but
I'm sorry. I didn't notice. Okay, I'm concluding within 5 minutes. Okay. So the next part is the qubit non-Markovian detection using Bell state. So we know that Bell states what it is. There are 4 Bell states in 2 dimension. So as you can see, the defacing channel in sigma z basis, and if we consider the Choi matrix here, so if we take the expectation of psi2 is basically, as you can see, this is the Bell state 0, 0 plus 1, 1 by root 2. If we take the expectation, this gives me gamma zt, and if it is negative, then the dynamics is non-Markovian, and if it is Markovian dynamics, we are having gamma zt to be non-negative for all t. So thus we can say that this Bell state can serve as a non-Markovian witness for 2 qubit case. We can also show this. These are the list of results that for dephasing in sigma x, dephasing in sigma y, and also the depolarizing channel, we can use the Bell states to detect the non-Markovianity in the same fashion. So in principle, that this is basically it uses a Bell state to detect non-Markovianity, and this is for amplitude damping channel, and this is for the thermal channel. I'll quickly go through the geometry of the Markovian part. The question arises whether we have shown that this is a convex set, but the next question arises whether it is polytope or not. Because if it is a polytope, then we could say that linear witnesses are enough to detect all kind of non-Markovianity. But we have shown that this convex and compact set under small time interval approximation, this is a convex set, but it is not a polytope because there are unitary dynamics, and unitary dynamics are basically Markovian. And unitary dynamics, the corresponding Choi matrices are basically the maximally entangled states. And so they are all pure states sitting inside the extreme points of the state space, and which are in the common region to the Markovian Choi matrix as well. So in light of this result, we can show that there are infinitely many extreme points for the Markovian Choi matrices, Markovian Choi state. So that is why it cannot have finitely many extreme points. So the structure is not a polytopic structure, it is just a convex set. And this actually gives us the way to, it's a nonlinear improvement of the witness theory, which will be considered by Anando next day. So there is a nonlinear improvement, it can be done with this. Since we are not having the polytopic structure, this nonlinear improvement can be done in principle. So these are some schematic diagram of this FM epsilon and the state space and the Choi matrices. So as a concluding remark, we would like to say that we have identified the backflow of information as a resource, and we have shown that this resource theory can be in principle constructed, and also show that it is the Markovian operations, they actually form a convex set under very small time interval approximation, and using that we can have the geometric Hahn-Banach theorem to show the existence of non-Markovian witness. And this we have given the examples on the qubit channels, And our actually construction gives us advantage in detecting eternal non-Markovity as well. And one of the important point is the non-Markovity can be detected, qubit non-Markovity can be detected by using Bell states. And the last point is that Markovian operations under small time interval approximation, though it is a convex set, it is not a polytope, and this gives us the idea that the nonlinear improvement of the witness can be done. Thank you very much. I'm sorry for the delay.
So Biholan, there are some questions
Yes.
in the chat box. So the first question is from Aditi Di. There is a recent paper by Kavan Modi which tells that completely positive divisible quantum process can still involve non-Markovian temporal correlations to make that as a free operation. So any comment?
We have considered only CP divisibility case. They have claimed to consider on a more general setting, but we have considered the traditional way of considering the non-Markovianity of CP divisibility case. So in our case, the CP indivisibility, it actually gives us the information backflow, and for the resource theoretic perspective, that's why I actually address that point, that why I'm taking the CP indivisibility as a figure of merit, because to have the information backflow, which is the resource in our case, this actually CP indivisibility is necessary for that. So that is why we actually go through this CP divisibility indivisibility in this scenario.
Okay. The second question is from Shiladitya Da. In resource theory of entanglement, Nielsen criteria dictates state convertibility. What is the analogous thing there?
Shiladitya, yes, this is a good question, but I have not explored in this direction. But I actually, what I should say here, there may be chance, but obviously in any resource theory, in general resource theory, there is a notion of convertibility of resources under free operation. But in this case, I actually do not know what is the exact mathematical structure or how to approach this. So at this point of time, I cannot answer this question. But okay, I'll definitely try in future to address this question.
So the next question is from Sharonath.
Yes.
Is it possible to construct a resourceful operation from a map which is not completely positive via structural physical approximation? In particular, is there any connection of this resource theory with the theory of entanglement detection?
Okay, so if we have structural physical approximation, okay, one point I would like to say here, that if the dynamics is CP indivisible, if it is not CP, if it is not CP divisible, but actually there is the direct connection of entanglement theory, I cannot tell right now. But the structural thing is basically similar to entanglement as well, so that we can see. But for the resource theoretic perspective, that is the question, if I understand the question properly, that how is it possible to connect the resource theory of entanglement to the resource theory of non-Markovianity? So in that way, I have to see.
Okay, there is no question, so let's thank Biholan.
Thank you.
Thank you, and you can stop sharing. Okay, so our next speaker is Shiladitya Mal from HRI Prayagraj. Shiladitya, are you there?
Hello, thank you.
Okay.
Am I audible?
Yes. Yeah, you can. You are audible. So
thank you, Nina, and thank you for this time the co-organizers. And I should mention that I go to various type of conferences, but this type of conference where only young persons, especially PDF and postdoc, took part in lecture. So it is a very different flavor with respect to the other kind of references. And I am glad to mention here that my first coming to HRI was in such an instant in the previous young quantum I came first here. So now I am moving to my talk. I am sharing a screen, my screen now. Can you share my screen?
Yeah, it's visible, but
Yeah, I want to
you
enter
have
the
to, yeah,
screen.
you have to enter the full screen. Yeah, now it's fine.
Okay, so let me start now. I may not, during my talk, I may not see chat box. Please, Noyana, tell me when last 5 minutes will be left.
Okay, fine.
So, in this talk, I will, this work actually based on one of my previous work. And here the co-author, Professor Aditi Shende and his researcher, Ratul and Srijan are involved in this work. So from the title, you can see there are very many concepts like non-locality, network, and quantum network, and overall spreading of non-locality in quantum network. So I will come to these topics one by one, including my motivation. So let me start with another acknowledgement that is in this modern in present time it is hard to emphasize the importance of the internet when we are conferencing through the internet, which is based on classical working of system, classical working of nature, which we call classical internet. And the figure cards I download many figures from the classical internet. So now everything so far we are doing through classical internet, and I am talking about what will be the feature if we can visualize about the quantum internet. So in classical network, the information is transferred through mainly electromagnetic wave. They are the carrier of the information. So zero bits, the classical bits are the carrier of the information. So it is there is a carrier signal. There may be noise, but with the instead with the in the presence of noise, the classical signal that is encoded in an electromagnetic wave, which is treated classically here, the encoded information in terms of 0 and 1, and similarly the figure of merit in the signal to noise ratio, which characterize the classical internet. Now this is the prototypical scenario of the classical internet, where from the sender a wave is propagated and it reflect to ionosphere, or it may reflect from some part of the earth and finally come to the receiver. And receiver, there is a decoding system that can decode the signal comes through the classical carrier. When we describe light or electromagnetic wave according to classical theory, the key parameter are the frequency, amplitude, and phase. You know all these things from your graduation time, and with this with this degree of freedom, with this classical description of light, we can encode information, and these are the two popular mechanism to encode information in classical light. That is amplitude modulation, which AM or FM, that is a frequency modulation. It is it is classical encoding of information. And also there is a polarization degree of freedom, which indicates the electric polarization vector, direction of the polarization vector. And unpolarized light passing through the polarizer become polarized light. And again, it has applications in the area of microscopic and display, any kind of display, laptop or mobile, or it can carry the information when signal is transferred to optical fiber. Now come to the quantum description of light. Let us see what is the quantum feature of the light. It is mainly the superposition and entanglement. The superposition, if we in quantum description of light, we have the power of manipulating even at the single photon level, or small number of or finite number of photon, we can manipulate the light at that level. And a single photon behaves as a single spin-half particle, where the polarization is the horizontal or vertical. It can have a state whether it can decide in a superposition of horizontal or vertical. And in the right hand side, you find the picture where the ultraviolet laser from the source of beta barium bored, the two conical trajectory of light overlap in the middle region, and the two dots indicate the true entangled photon. So utilizing this feature of light, that is called quantum nature of light, let us see what we can have, what we cannot have with the classical light or the classical description of light. It is a new generation of quantum technology. Now we are at the present time at the era of second generation of quantum technology, which mainly rely on this kind of feature which I just described. And relying on this feature, we have many technologies like quantum computing, quantum simulation, quantum key distribution, quantum number generator, quantum computing, imaging, metrology, and so on. Now I focus on the quantum network. Here it is a timeline the goal set by some European scientists, though they are finally they are heading to establish in a quantum computer. But before that, we are heading to the quantum internet. So in that, let me formally define what this quantum internet means. A network, any network is a collection of nodes, and ability to share information among the different nodes, that is the different parties situated at different location, is the basic building block for a communication network. The information which is distributed through this channel may be classical or quantum. In both cases, it was shown that entangled state shared between the senders and receivers can enhance the performance of the protocol, which cannot be achieved by unentangled state. Now here is a picture taken from the work by a group of Jioming Pan, where they established the satellite-based QKD between different locations which are apart 1200 kilometers. And from satellite entangled source, one of the entangled source is sent to one place and another is sent to the another place, which are apart from 1200 kilometers. Now let me move on to what you know, but for the sake of completeness, let us define what do we mean by entanglement. That is the for pure state case, it is the state, either the quantum state which cannot be written in a product form, or it can have mixed state in representation where they can be written as a convex mixture of product state. Or operationally, we can also define it in a way that if two observers, say Alice and Bob, are separated in different distant labs, and with the only operation, allowed operation, that is classical local operation or classical communication, only with those kind of operation, they only can create separable state. They cannot create any entangled state. So this entanglement is manifested through the Bell violation of Bell inequality. Now, what is Bell non-locality? It is a kind of test of non-classicality, or it can be said that it is a certification of the entanglement from minimal assumptions together with the observed statistics collected in a laboratory. So observe the minimal assumptions here, we require two assumptions, that is the no signaling, which is maintained by separating the two observer in a space-like distance. Here is the source, from source to entangled particle, one come to Alice and one come to Bob, and they are separated in a space-like manner. This enforces the no signaling constraint. And another assumption is the measurement independence, where Alice here can randomly change her setting. That is, she can orient her direction in some X direction or orient her device along Y direction. So that random change of setting is independent of the variable carried by the source. If there is some variable which dictates the property of the particle, then it is independent of that variable. So this is called measurement independence. So under these two assumptions, with the statistics collected at the coincidence detected, the joint statistics is the joint probability distribution. And only with this thing, one can certify the underlying entanglement. So in a nutshell, this is the Bell test. It is a special kind of test, not it is the any usual form of test. Now it can be think that there can be many particles. Instead of 2 particles, there can be 3, 4, and so on. So from the source, 3 particles goes to 3 different detectors. It can be 4, 5, and similarly we can test non-locality or Bell non-locality in the multipartite settings. Now, for bipartite case, it is the CHS inequality, where the settings of Alice can be A1 and B1, and from bauxite can be B1 and B2. It is a two settings and 2 outcome experiment, where the known CHS inequality is the Bell inequality here, and the expectation value are obtained in this way from the and for multipartite setting, we have the Marmin-Belinsky and Klasko inequality, the NBK inequality, where here is the corresponding Bell operator is the here, and BK and BK is defined in a recursive way, where BK1 minus 1 prime is obtained by changing sigma AK to sigma AK prime. It is recursively defined for n is the number of party. So now the inequality is the mod of this should be greater than 1. For multipartite system, there is another inequality which is very essentially different from the other two notions of Bell inequality, that is introduced by Zhukovsky, that is called functional Bell inequality, which is the other two we have different setting, Bell inequality for 2 particle and MBK inequality for multi-party. But here, this multi-party functional Bell inequality is in different, it is essentially different from the previous two. Let me briefly define how it is obtained. So again, here we have quantum correlation between the n party. Rho n is the n party state, and G1 to Gn is the local measurement performed by the local parties. And again, we have local variable model correlation is captured in this way, where In it can depend upon the measurement parameter. Eta is the measurement parameter, and lambda is the variable, local variable carried by the particle. So with this description, it is the local variable model description. We have an overlap between the quantum correlation and the local variable description of the correlation. Now this overlap indicates the how much quantum correlation matches with the overlap correlation comes from the local variable model. And again, we have mod CQ square, which is actually considered the continuous setting of the parameter of the measurement. In other case, in previous case, Bell case, we consider only 2 settings. For Marmin, Belinsky and Klasko case, we consider many settings, but finite setting and special settings are required. But in case of FB, we consider continuously varying settings, and this mod CQ square is defined integrating over, averaging over all the continuous setting range of parameters of the measurement device. So with this quantity, we can define functional Bell inequality, which is the inequality, the overlap mod of the overlap between the quantum and the local variable correlation is less than 4 to the power n, where capital N is the number of particles. And for GHG state, the maximum value of the quantum correlation is given by 2 pi to the power n by 2, which is obviously greater than 4 to the power n, exhibiting the quantum non-locality. So main motivation of this Bell inequality is this: in the interferometric Bell setup, interferometric setup of Bell test. So these inequalities provide better robustness, and the violation grows more with the n, with the number of party with respect to the MBK inequality. With increase of n, functional Bell inequality give more and more violation with respect to MBK. Now, let us come to how we implement these ideas in the case of quantum net. Here, now is how to establish quantum internet and to check whether this quantum internet is established or not. For a little digression, I will talk about the quantum repeater. It is a popular and well-known way of establishing a repeater. So it actually is a system where a long distance entanglement can be established, correlation can be established between two distance observer, where the total distance can be divided in different small segments, and these are the small entangled system. So come from a common source. There are many sources, and they send entangled particle to a little distance, and they make a long distance chain, where in the middle this indicates the joint measurement. So in here the entangled state, if the entangled state are the maximally entangled state, after the performing the joint measurement indicated by the blue arrow, finally the experiment, that is S and R, there is a maximally entangled state can be established between S and R. So this is a way of establishing the maximally entangled state with the help of other maximally entangled state which are distributed within short range. So within with the short range distributed entangled state, we can have a long range distributed entangled state. But the shared entangled state may not always be maximally entangled. As this from the source it comes to the environment, there may be noise. So in that case also, we have to incorporate another idea of purification or distillation of entanglement, which is actually make maximally entangled state out of some non-maximally entangled state. So in that case, here will be many copies of non-maximally entangled state, and every segments they share many copies of non-maximally entangled state. Finally, they will follow some distillation protocol to purify it, and after then swapping experiment will be done. This is a swapping measurement experiment, and finally we have the entanglement between S and R, and finally even we can have in this way many entangled state between S and R, and again finally we can purify to a maximally entangled state. So in a nutshell, this is how the quantum repeater works to establish long distance entanglement. But here you can be it can be noticed that there are many problems that you may have many copy. This involve the distillation protocol. So this is a little bit involved process. Now here we are proposing a different way of establishing network, which is measurement based network, different from the quantum repeater model, where we do not have to need to have many copies or distillation protocol. We have only single shares. I will come to the protocol details later. Where we do not have to need such kinds of many process or distillation process. So first we will establish network through the combination of global and local measurements, and local measurements can be collaborative and non-collaborative as well. And then whether the network is established at all, that is whether verify to whether network works, we apply the Bell test in the for the appropriate scenario, which is appropriate scenario. And in that purpose, we introduce the notion of localizable non-locality. So what is this? So this is the basic building block of to establish a network. The basic building blocks is this. Here, the initially we have the bipartite state connected by the line, and in the blue dot where they all come form a node where a single observer can possess all these blue dots, and the outer are the distant points. So for example, you can consider that these bipartite set connected by the line can be some noisy Warner state. It can be for p equal to 1, it is a perfect singlet state, otherwise it is a noisy state. So this network can be built out of from noisy entangled state. Now the red circle indicates the global measurement can be done here in the node. The global measurement, and after the global measurement indicated by red dot on the all the blue points, the outer outer parties are get correlated. This red portion got out of the correlation, and finally the outer circle point at the outer circle, all they get correlated. So in that way, we have a connection between quantum connection between the outer circle, which points and the outer circle, which were initially uncorrelated. And here you can find, again, we can employ the blue. After that, we can employ the local measurement on this point, where arrow on the green dot implies we can employ some local measurement in some direction. And finally, we can have a correlation between two yellow points. So we can fix any set of points, and we can, if we want to establish correlation between two yellow points, it can be any other point. Then we do not apply local measurement on those. We apply local measurement except on those 2 points on the other points. So with this measurement technique, we have a localizable non-locality. That means we sweep the correlation between the two yellow points with the combination of first global measurement and then the local measurement at the appropriate point. So finally, we have the final output state. We will define the average Bell violation, the Bell inequality. If we have the final output state is a two-party state, we will consider the CHSH inequality. And we have the, using the Horodoki formula, we can find the maximal violation of CHSH inequality. And the local measurement have the very different combination of outcome. And if we average over the all different combination of outcome and consider the Bell violation of those output state, and this give the average Bell violation over the local measurement outcome. We call this quantity as the localizable non-locality, and it will be our figure of merit to check whether the connection has established or not. Now with these ideas, we come to the example. If we have a three part, only the three, initially we have the three one nested three pair of particle. Then the GHG basis measurement, actually we have the 8 orthogonal bases. So these are the 8 state. These form the GHG basis measurement for three on three party. And after the central GHG measurement, the final outer party state will look like this. This is another state, three-party correlated state, which is mixed with GHGZ. There will be a white noise and color noise, and Q1 are the function of P. P is the initial noise parameter. And the local measurement are in some direction of theta phi. Here, the local projective measurement, this indicates by the parameter theta and phi. Now, after if we, the another concept here is the notion of super additivity of non-locality. It is actually introduced in 2005, a paper of
Shiladitya.
Yes.
Hello. So you have 5 minutes left.
Okay. So this notion of super additivity means if the initial one state of the building block is noisy, does not show the violation of CHS inequality, then the final output state obtained through the combination of global and local measurement can have violation of CHS inequality. And it was shown that if the initial we have a pair more than 7, we can have this kind of activation of non-locality, which is called super additivity. Now, with these ideas, if we consider the star network, this is called star network, we have found that this is the equation which dictates the critical value of the initial noise. For n equal to 3, solving this equation, we find that pre-critical is a 0.869. That means if the initial Warner state have P greater than this, we can have the CHS inequality violation after the localization of the correlation between two yellow points. And it is for the case of more than two party, we consider, as I mentioned previously, the Marmin inequality here, Marmin Belinsky cluster inequality here, And this is the another form of the same MBK inequality. The maximizing over the local measurement, we have the condition. Again, we can find the condition of pre-critical. And similarly, if we consider the functional Bell inequality, which I explained previously, we again can find a critical value here. So this is the graph actually in a nutshell compare that the functional Bell inequality in performs better than the Marmin-Belinsky-Glasgow inequality in the case of multi-party. So here the red line indicates the MBK and the green dots indicate the functional Bell inequality, which the increase the x-axis indicates the number of party and x-axis is the critical noise. So with the increase of the party, you can see that the critical noise required for the violation of the corresponding inequality is less in the case of a functional Bell inequality with respect to MBK inequality. Now, with this idea, it is a straightforward extension how to establish a long network. For the example, for here we have 1D network. The same building block is repeated. Here in the circular region, we employ global measurement. And finally, the outer part of these are correlated. And we can fix, suppose here 1, 2, 3, and 4, we want to create a correlation, then we have to measure locally on the other point. So in this way, here we have the two other parameter. A is the coordination number, means what is the number of particle in the node, and J is the number of nodes, that means how many building blocks are here. Depending upon the A and Z, we can have a pre-critical which appear in the equation. We can again solve for the value of pre-critical, and we can find in that case again the super additivity arises when the coordination number is greater than equal to 6 for any arbitrary number of nodes. And again here we find that functional and MBK and FB inequality have the greater performance over the CHSH inequality. So blue dot here indicates CHSH and green dot here FB, that with the increase of A, it requires the less noise to reveal the non-locality in the network. Here, 1D network, we can establish a 2D network, which is actually the lattice of bipartite state. Again, applying the idea of 1D network, we can again prefix some point to make it correlated. We have to make the global measurement here. In this way, we can connect these yellow points A, B, C, and D. To do this, we have to make global measurement in between in the circle, and finally we have to measure locally here. So we in 2D we can have also different type of geometry. Here is the square lattice, here is the triangular lattice. But the important thing to note is that in case of square lattice, as the coordination number is less than 6, we cannot have super additivity. But in triangular lattice, we can have coordination number 6, and in that case, we find that super additivity can be activated. So geometry also play an important role to find to achieve super additivity. So now I've come to my last slide, that is the conclusion. We establishing large network distributed over many distant sites is a challenging and a desired task. With increasing size of the network, it is very difficult to verify whether the quantum connection is established or not. We propose a protocol based on the combination of global and local measurements to establish large network. We employ Bell test appropriate for the scenario to certify quantum connections under minimal assumptions. Suitable geometry of the network has been found for exhibiting super additivity of non-locality. And thank you for your attention.
There are some questions. So the first question is from Kopil. He asks that consider a network of two computers. So in your case, how you define the quantum networks between two computers? Are you considering the quantum connection between two classical computers or the quantum connection between two purely quantum computers? Can you please give the light on both the cases and how you think that a quantum analog can be developed on TCP or IP protocol?
So here we define the nodes and the connection is established between the different nodes. So the implementing process, you can think if in a quantum computer, you can establish a network. In a processor, there are different components which are at different location. In the case, if we want that within a computer hardware, we have to establish network between different part of the processor. Then how to establish? We have tested. Again, you can think that the nodes are distributed in a globally. Then one in Vienna and in Allahabad, one in Kolkata, one in Varanasi. Then you have to establish the quantum connection between those different points which I separated. So it can be within a hardware of the computer, or it can be a globally connect network. And the protocol we define how to establish it can be any different computer within the computer or different space of the art. It can be.
Okay. Yeah. The next question is from Arijit Datto. Is functional Bain inequality tight?
What is a tight means here? Okay.
I didn't mention.
If tight means that it is the necessary and sufficient in the spirit of CHSH inequality, not a single CHSH inequality is not necessary and sufficient, but only sufficient. If we consider all the CHSH inequalities, is provide a necessary and sufficient condition. That means violation of CHSH inequality indicate non-locality, and satisfaction of all the CHSH is one can construct a local model. But with two settings. So in the functional Bell inequality, we do not have finite number of settings. Rather, we consider the continuous range of settings. And when the quantum, it indicates when the quantum correlation is different from the correlation dictated by local variable. So if they differ, we can say that the non-locality is detected. But if they are same, we cannot say about the correlation. In that sense, we can say that it may not be tight. If the overlap between the quantum correlation and correlation described by local variable is equal, then we cannot say that the correlation can be actually there is some local model or not.
Okay, so the next question from the same guy is how noise can reveal non-locality?
How noise can
reveal non-locality?
How noise can reveal noise cannot reveal non-locality. Noise reduces non-locality. We can say that instead of noise, what is the max threshold value of noise? Instead of that amount of noise, we can reveal non-locality. If we have maximally entangled sets, CHSH inequality violate maximally. But if there is some noise, the amount of violation reduces. Now the question is, what amount of noise can be tolerated to get some violation of inequality?
Okay, so then another question is from Kapil. Do you have any quantum analog of TCP or IP? If not, then how do you claim?
What is DCP IP?
TCP or IP? You can check the chat box.
TCP.
TCP.
Okay, I'm checking.
I think he is talking about the network, probably classical one, right? TCP IP.
TCP for internet.
Yeah, in the internet. I think what Shiladitya has mentioned that, I mean, I can add, right? So the point is that we first want to establish just the entangled state connection. So if we have two computer or more computers, we first connect it. We first address the questions how entanglement can be shared over the network. This is the questions that we have addressed. Now, after the sharing has been done, you can use for classical information transmission or the quantum state transmission, because we know you can perform dense coding type protocol, key distribution, or the teleportation type protocol. This we don't talk about. We just ask, as Shiladita mentioned in the first slide, he first discussed that how to establish connections, entangled connections, or how to establish entangled channel between several nodes which are somehow in a different, in distant locations. This is one thing. And second thing is that we address how to detect whether really the nodes are entangled. And for that, we use belt test. We don't talk about the internet, how that is, I think, under probably people are also doing research. It's not clear as yet.
Okay. So,
Okay, any other question?
no, there is no other question.
Okay, so if there is no other question, then we should. Okay, so Kopil may have questions. We can talk after this talk and after this sessions. You can be online. We will be online for some time. So let's finish the morning session and we really thank Anu Kumari from Delhi Technological University and Noina Dash from ISI Kolkata for chairing nicely both the sessions in the morning. And we also thank all the speakers in the morning. So we will see each other again at 4:30 p.m. when we start our afternoon session. Kothakoli will be chairing the session, and I think the first talk is by Aravinda. And we also have the Sharonath's talk, and as well as poster presentation. And then we have a keynote talk. So for now, we vanish and we meet again at 4:30. But if people have some questions to the speakers, now can be directly asked, right? So speakers can stay for a few minutes. If anyone has a questions who are in the audience want to ask something, can ask, right? So that you can have discussion. So this Zoom thing will be on. And we can stop live streaming, Chandan.
Okay, ma'am. I'll stop this YouTube.
Yeah. Wait 5 minutes more. If someone wants to ask any question, even who are listening in the YouTube, they can still type questions to the speakers. Speakers are still online, I think, all of them in the morning sessions. They can stay 5 minutes. If someone has a questions which they want to ask, they can ask.
I think, hello, Kopil has they write some question, can.
Yeah, maybe if you can answer to Kapil's question if you want. He has this question about TCP/IP protocol.
Kopil can clarify what you are asking. What I am claiming that if you have to establish correlated system between different parties, and TCP/IP claim I do not claim, but so you can, if you can clarify your question, I can write or tell. I do not claim anything about TCP/IP claim. So where if you can clarify a little bit more, then it will be better to give a better answer.
Maybe Kapil is there, or I don't know.
If you have a question not regarding my talk, you just Google. Do you want to know the concept of packet in the context of internet? So I think you are saying something which I do not tell.
So I think he is asking about the internet thing, which I think we don't address.
You just ask what is I said.
Something is going on.
I think he said okay, but his question is something other. I can end here.
Yeah, you can discuss with him personally, but maybe not.
Sure.
Yeah, Chandan. Hello, Chandan.
Yes, ma'am.
Yeah, you can stop at 12:30 maybe. The live streaming you can stop now also if there is no other questions of Shoptashi and Chirag.
No, there are no questions anymore.
Yeah, so you can stop live streaming and people can be few minutes in the. I mean, they can also chit chat. I mean, there's no point.
Sure, I'll do that. Okay.
You stop live streaming so that people can discuss something.
Fine, just a second. I'm doing it.
Also, recording can be stopped.
And there are no more questions from YouTube.
Yeah.